Let's be honest about something right from the start. It's New Year's Eve, or maybe it's already New Year's Day, and you're here, listening to a stranger talk about space for 5 hours. That's either the best decision you've made all year, or you've already given up on the concept of good decisions entirely. Either way, welcome. I'm genuinely glad you're here. Here's what's about to happen. For the next 5 hours, we're going to explore the most unhinged, genuinely absurd, scientifically verified facts about the universe. And I need you to understand something crucial. I'm not making any of this up. Every single thing you're about to hear is real, peer-reviewed, published in actual scientific journals. The universe is not serious. It never has been. And tonight, we're going to prove it. You're probably expecting me to ease you into this gently. To start with some comfortable facts about the moon, maybe talk about constellations, build up slowly to the weird stuff. We're not doing that. We're jumping straight into the deep end because the universe doesn't do gentle introductions, and frankly, neither should we. Let's talk about Uranus. I can already hear you smirking. The planet has heard all the jokes. Scientists named it in 1781, and humanity has been giggling ever since like a planetary-scale middle school classroom. But here's the thing that nobody tells you. Uranus is genuinely, scientifically, objectively hilarious for reasons that have nothing to do with its name. This planet is giving chaos energy on a level that would make reality TV producers jealous. First, Uranus rotates on its side, not tilted, not slightly off-axis, completely sideways. Imagine if Earth did this. Summer in New York would last 21 years, winter would also last 21 years, you'd graduate college, get married, have kids, start a career, go through a midlife crisis, and the sun still wouldn't have set on your hometown. That's one season. One. The poles of Uranus experience 42 years of continuous daylight, followed by 42 years of complete darkness. No cap, if you lived on Uranus, you could be born in summer and die of old age without ever experiencing winter. But that's not even the funny part. Scientists genuinely got research funding to study what Uranus smells like. I'm not making this up. In 2018, a team of researchers pointed spectroscopes at Uranus, analysed its atmospheric composition, and discovered significant quantities of hydrogen sulfide in its upper atmosphere. Hydrogen sulfide. The same compound that makes rotten eggs smell terrible. The same compound that makes farts smell like farts. Someone has studied what Uranus smells like on their actual CV. That's a real job someone did. With grant money, tax dollars went toward confirming that Uranus smells like farts. And here's where it gets even better. The paper was published in Nature Astronomy, one of the most prestigious journals in the field, which means it went through peer review, which means multiple scientists had to seriously evaluate a paper about Uranus smelling like farts and conclude, yes, this is scientifically rigorous, this deserves publication. Somewhere, there's a peer reviewer who wrote comments like, the methodology for determining atmospheric composition is sound, while describing fart planet research. This is what I mean when I say the universe is unserious. But Uranus is honestly just the appetizer. Let me tell you about Neptune, because if Uranus is chaotic, Neptune is giving full supervillain energy. Neptune has winds. This isn't news. Lots of planets have winds. But Neptune's winds move at 2,100 kilometers per hour. That's not a typo. 2,100 kilometers per hour. That's faster than the speed of sound. Neptune has supersonic winds. For reference, the fastest winds ever recorded on Earth were about 408 kilometers per hour during Tropical Cyclone Olivia in 1996. Neptune's winds are 5 times faster than that. They're so fast they break physics in ways that scientists still don't fully understand. Here's the problem. Neptune is cold. Extremely cold. The average temperature on Neptune is minus 214 degrees Celsius. It's so far from the Sun that it receives almost no solar energy. Earth gets about 400 watts per square metre from the Sun. Neptune gets 1.5 watts, and yet somehow Neptune generates winds that make Earth's most violent hurricanes look like a gentle breeze on a spring afternoon. Where is the energy coming from? We don't know. Neptune is producing more energy than it receives from the Sun, and we have theories, but no definitive answers. Neptune is literally doing things that shouldn't be possible, and it's doing them at supersonic speeds. Neptune is also incredibly blue. Not metaphorically, not kind of blue, aggressively, impossibly blue. Bluer than any ocean you've ever seen. Bluer than the sky on the clearest day. This planet is serving blue raspberry slushy aesthetics on a cosmic scale, and the colour comes from methane in its atmosphere absorbing red light. But here's what gets me. When Voyager 2 flew past Neptune in 1989, scientists expected it to look like a slightly more colourful Uranus. Instead, they got this impossibly vivid blue marble that looked like someone maxed out the saturation slider in Photoshop. Neptune said, "I'm going to be the bluest thing in the solar system and nobody can stop me." And it was right. Let's stay with the ice giants for a moment, because we need to talk about the fact that both Uranus and Neptune probably have oceans, not on their surfaces, inside them. Deep inside their interiors, beneath thousands of kilometres of hydrogen and helium atmosphere, scientists believe there are oceans of liquid water mixed with ammonia and methane. These oceans are under such extreme pressure that they're not like anything we have on Earth. The pressure is so intense that it could theoretically compress carbon into diamonds, which means that deep inside Uranus and Neptune, it might be raining diamonds. Let me say that again. It might be raining diamonds inside these planets. Large diamonds, potentially. Scientists have run simulations and lab experiments suggesting that, at the right depths, carbon compounds could crystallize into solid diamond and fall like rain through these bizarre interior oceans. There could be diamond icebergs floating in subsurface oceans on planets so far from Earth that their existence feels almost imaginary. The universe really said, "You know what would be funny? If we made it rain diamonds on a planet humans will probably never visit." And then it did exactly that. Now let's talk about exoplanets, because if you thought our solar system was unhinged, wait until you hear about the absolute chaos happening around other stars. There's a planet called HD 18733b. It's a gas giant about 63 light years from Earth, orbiting very close to its star. At first glance, it looks beautiful. Deep blue, similar to Neptune, absolutely gorgeous in images. And then you learn literally anything else about it and realise this planet is giving beautiful but deadly energy on a level that evolution couldn't have prepared us for. HD 89733b has glass rain. Not water rain, not acid rain, glass rain. Molten silicate particles condense in the planet's atmosphere and then fall as glass, but it doesn't fall straight down, because HD 89733 has wind speeds of about 8,700 km per hour, so the glass doesn't rain down, it rains sideways, at 8,700 km per hour. This planet has sideways glass rain moving at Mach 7. Imagine standing on HD T9733b. You can't because you'd be instantly destroyed, but imagine anyway. You're being sandblasted by glass shards moving 7 times the speed of sound, while the ambient temperature hovers around 1000 degrees Celsius. This is what the universe considers a planet. This is a real place that exists, and we named it HD 18733b, which is possibly the most boring name we could have given to Glass Hell Wind Planet. Here's another one, WASP 12b. This planet is so close to its star that it's being actively eaten. The star's gravity is pulling material off the planet's atmosphere. WASP 12b is egg-shaped because it's being stretched by tidal forces. It's losing mass at a rate of about 6 billion tons per second. That's not a sustainable business model. Scientists estimate that WASP-12b has about 10 million years left before it's completely consumed by its star. This planet is literally dying in real time, and we're watching it happen. The universe created a planet just to kill it slowly over millions of years while we take notes. Then there's TRIS-2b, which holds the distinction of being the darkest known planet in the universe. It reflects less than 1% of the light that hits it. It's darker than coal, darker than acrylic paint, darker than the blackest material humans have ever created. This planet absorbs almost all light that touches it, and scientists don't fully understand why. Current theories suggest it's because of atmospheric chemistry involving vaporized sodium, potassium, and titanium oxide, but we're basically guessing. TARI-S2b looked at the concept of reflection and said, "No thanks, I'm going to absorb everything and give nothing back," and it committed to that aesthetic completely. But my personal favourite exoplanet has to be J147b. This planet has rings. That's not unusual. Saturn has rings, Jupiter has rings, Uranus and Neptune have rings, but J147b has rings on a scale that makes Saturn look like it's not even trying. JK14-b's ring system is approximately 200 times larger than Saturn's rings. If we replace Saturn with J1407b in our solar system, its rings would be easily visible from Earth with the naked eye. They would dominate the night sky. They would be brighter than the moon. J14-b's rings contain roughly as much mass as Earth. The entire Earth. Just in rings. And here's the thing. We don't know if J1407b is even a planet. It might be a brown dwarf, which is like a failed star. We discovered it because it passed in front of its star, and the star's light dimmed for 56 days. 56 days. That's how long it took for this object's ring system to transit. For comparison, when Earth passes in front of the Sun from the perspective of a distant observer, the transit lasts about 13 hours. J1407b's ring system is so absurdly large that it took almost 2 months to move past its star. The universe really said, "You like rings? Here's a planet that's basically all rings with a small planet attached as an afterthought." Let's pivot to something that sounds made up but isn't. Rogue planets. These are planets that don't orbit stars. They just drift through interstellar space, alone, in the dark, going nowhere in particular. They're cosmic homeless, and there are a lot of them. Current estimates suggest there might be billions of rogue planets in our galaxy alone, possibly outnumbering stars. How does a planet become rogue? Usually through gravitational interactions during the formation of a solar system. Picture this. You're a planet, minding your own business, forming an orbit around your nice warm star. Then another planet swings by, or maybe several planets get into a gravitational argument, and suddenly you're ejected from the system entirely. You're thrown out into interstellar space at tens of thousands of kilometers per hour, and you just keep going. Forever. Your star is gone. Your neighbouring planets are gone. You're alone in the void, and you will be alone for billions of years until maybe, possibly, you pass close enough to another star to get captured by its gravity, but probably not. Probably you'll just drift forever. And here's the deeply unsettling part. Some of these rogue planets might have moons. They might even have oceans under icy crusts, kept warm by tidal heating from their moons and residual heat from their formation. There could be life on these planets. Not complex life, probably, but microbial life existing in subsurface oceans on planets that don't orbit any star, drifting through the absolute emptiness of interstellar space. Life that evolved in complete isolation, with no sun, no solar system, no context for where it is or why it exists. The universe created planets, kicked them out of their solar systems, and then said, "Figure it out yourselves." And some of them might have figured it out. Now let's talk about something that bothers me on an existential level. The speed of light is slow. I know that sounds absurd, Light travels at 299,458 meters per second. That's fast. That's incomprehensibly fast by human standards. But on cosmic scales, light is slow in ways that break my brain every time I think about it. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's how long light takes to travel from the moon to your eyes. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. If the sun exploded right now, we wouldn't know for over 8 minutes. We'd just be sitting here, thinking the sun still exists, completely unaware that our star had ceased to be. We get another 8 minutes of sunlight from a sun that was already gone, but that's nothing. When you look at Alpha Centauri, the nearest star system to us, you're seeing it as it was 437 years ago. When you look at the North Star, Polaris, you're seeing it as it was 323 years ago. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. You're looking at light that began its journey to your eyes before humans existed in our current form. You're seeing prehistory. The photons hitting your retina right now started travelling before Homo sapiens had even evolved. And it gets worse. The observable universe is about 93 billion light years in diameter, but the universe is only 13.8 billion years old. How is the observable universe bigger than the age of the universe multiplied by the speed of light? Because space itself is expanding. The fabric of space-time is stretching, and it's stretching faster than light can travel across it. There are galaxies moving away from us faster than the speed of light, not because they're travelling through space that fast, but because the space between us and them is expanding, which means there are parts of the universe we will never see. Not because we don't have powerful enough telescopes, not because we haven't figured out faster than light travel, but because those parts of the universe are moving away from us faster than their light can ever reach us. The photons are trying. They're travelling toward us at the speed of light, but the space between us and them is expanding faster than they can cross it. They will never arrive. We will never see those galaxies. They exist, but they are fundamentally inaccessible to us, forever. The universe is so large that parts of it are permanently hidden from us by the limitations of physics itself. Let me give you another example of how distance breaks everything. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's about 24 billion kilometers away. It's in interstellar space beyond the influence of the sun's solar wind, travelling through the void between stars, and it takes about 22 hours for a signal from Voyager 1 to reach Earth, 22 hours for a radio signal travelling at the speed of light. When NASA sends a command to Voyager 1, they send it, and then they wait 22 hours to find out if the spacecraft received it, and then they wait another 22 hours for the spacecraft to send back a response. That's a 44-hour communication delay for an object that's still in our immediate cosmic neighbourhood. Voyager 1 hasn't even left the Milky Way. It's still in our galaxy. And it already takes 2 days to have a conversation with it. Alpha Centauri, the nearest star system, is 4.37 light-years away. If we sent a message to a hypothetical civilization there, it would take 4.37 years for the message to arrive, and another 4.37 years for their response to reach us. That's a 8.74-year round-trip communication delay. You could send a message, graduate college, start a career, and then finally receive a response. And that's the closest star system to us. The universe is not built for conversation. Let's talk about neutron stars, because these objects are giving, what if we took physics and made it completely unhinged? Energy on every possible level. Neutron stars are the collapsed cores of massive stars that exploded in supernovae. When a star runs out of fuel, it can no longer support itself against its own gravity, and it collapses. The outer layers explode outward in a supernova, one of the brightest events in the universe. The core collapses inward, and if it's the right mass, it becomes a neutron star. Here's what that means in practice. A neutron star is an object with about 1.4 times the mass of the Sun compressed into a sphere about 20 kilometers across. 20 kilometers. The Sun is 1.4 million kilometers in diameter. A neutron star takes all of that mass and compresses it into something the size of a city. The density is so extreme that a single teaspoon of neutron star material would weigh about 1 billion tons. A teaspoon. If you somehow scooped up a teaspoon of neutron star and brought it back to Earth, it would immediately fall through the ground, through the Earth's crust, through the mantle, through the core, and out the other side, oscillating back and forth through the planet like a hyperdense pendulum until it settled at the centre. Neutron stars have gravity that makes black holes look chill by comparison. Well, not really. Black holes are still more extreme, but neutron stars are absolutely not messing around. If you were standing on the surface of a neutron star, you would weigh about 200 billion times what you weigh on Earth. The escape velocity from a neutron star is about 1/3 the speed of light. You would need to be travelling at 100,000 kilometers per second to escape. For reference, the fastest human-made object, the Parker Solar Probe, travels at about 163 kilometers per second at its fastest. You'd need to be going 600 times faster than that. But the truly unhinged thing about neutron stars is how fast they spin. Some neutron stars, called pulsars, rotate hundreds of times per second. The fastest known pulsar, PSR J1748 244 AD, rotates 716 times per second, 716 times per second. The surface of this neutron star is moving at about 24% the speed of light. Material on the equator of this pulsar is travelling at 70,000 kilometers per second. This object is spinning so fast that it's approaching the theoretical maximum rotation speed before it would tear itself apart from centrifugal force. And here's the thing, we can hear them. Pulsars emit beams of radiation from their magnetic poles, and as they rotate, these beams sweep across space like cosmic lighthouses. When the beam points toward Earth, we detect a pulse of radio waves. This happens with perfect regularity. Pulsars are among the most precise clocks in the universe. Some of them are more accurate than atomic clocks. When astronomers first discovered pulsars in 1967, they were so regular that researchers briefly considered the possibility that they might be artificial signals from alien civilizations. They called the first pulsar LGM-1 for Little Green Men 1. Spoiler alert, they're not aliens. They're just neutron stars being absolutely extra about everything. Let's talk about magnetars, which are neutron stars that decided regular neutron stars weren't extreme enough. Magnetars have magnetic fields about 1,000,000,000 times stronger than Earth's magnetic field. 1,000,000,000,000. If you were within 1,000 kilometers of a magnetar, its magnetic field would be strong enough to disrupt the molecular bonds in your body. You wouldn't be crushed by gravity. You wouldn't be vaporized by radiation. You would simply cease to be held together at a molecular level. The atoms in your body would forget how to bond to each other. You'd come apart like a biological Lego set, and occasionally magnetars have what scientists call starquakes. The crust of the neutron star, which is incredibly rigid because of the extreme density and magnetic fields, will crack. These cracks release enormous amounts of energy. In 2004, a magnetar called SGR 1806-20 had a starquake that released more energy in 1/10 of a second than the Sun releases in 100,000 years. The burst of gamma rays from this event was so intense that it measurably affected Earth's ionosphere from 50,000 light-years away. This magnetar halfway across the galaxy burped, and it changed the chemistry of Earth's upper atmosphere. The universe is not subtle. Now let's talk about black holes, because we can't do a Space Facts video without talking about the universe's most dramatic objects. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. We all know this. It's the defining feature of black holes. But here's what people don't always understand. Black holes don't suck things in like a vacuum cleaner. They're not cosmic hoovers roaming around eating everything. If the sun suddenly became a black hole right now, Earth would not get sucked in. We just orbit the black hole exactly like we orbit the sun now, because the mass would be the same, and gravity depends on mass and distance, not the type of object. Black holes only suck things in if you get too close. There's a boundary called the event horizon, and if you cross it, you're done. You're not coming back. The escape velocity inside the event horizon exceeds the speed of light, which means escape is literally impossible according to the laws of physics. But outside the event horizon, black holes behave like any other massive object. Here's where it gets weird. Time dilation. As you approach a black hole, time slows down relative to someone far away. This isn't theoretical. This is confirmed physics. If you fell toward a black hole while your friend watched from a safe distance, your friend would see you slow down as you approach the event horizon. They'd see you move slower and slower, your movements becoming more sluggish, until you appeared to freeze completely at the event horizon. Meanwhile, from your perspective, nothing unusual would happen. You'd fall right through the event horizon and continue toward the singularity. But here's the really messed up part. From your friend's perspective, you never actually cross the event horizon. They see you frozen there, red-shifted and dimming forever. From your perspective, you've already crossed it and you're being torn apart by tidal forces. Both perspectives are equally valid. You simultaneously cross the event horizon and never cross it, depending on who's observing. This is what relativity does to causality. It takes the concept of what happened and turns it into what happened from whose perspective. Let's talk about spaghettification, because it's called that, and it's exactly what it sounds like. If you fell into a black hole feet first, the gravity at your feet would be stronger than the gravity at your head, because your feet are closer to the singularity. This difference in gravitational force is called a tidal force, and it would stretch you vertically. While compressing you horizontally, you'd be pulled into a long, thin shape like spaghetti. For a small black hole, this would happen outside the event horizon, which means someone could theoretically watch you get turned into human pasta. For a supermassive black hole, like the ones at the centres of galaxies, the event horizon is so large and the tidal forces are so gradual that you could cross the event horizon without even noticing. You'd be fine, still in your normal shape, falling toward the singularity, and you'd only start to experience spaghettification closer to the centre. Which raises a horrifying question. If you fell into a supermassive black hole, how long would you survive inside the event horizon before the tidal forces killed you? Scientists have calculated this. For Sagittarius A, the supermassive black hole at the centre of the Milky Way, you'd have about 16 seconds from crossing the event horizon to reaching the singularity. 16 seconds of existence inside a black hole, knowing that you are fundamentally trapped and that your death is not just inevitable, but already predetermined by the geometry of space-time itself. 16 seconds to contemplate the fact that you have left the universe. Now let's talk about Hawking radiation, because black holes apparently weren't weird enough. Stephen Hawking figured out that black holes aren't actually perfectly black. They emit radiation, very slowly. Very, very slowly. Here's how it works. Quantum mechanics says that empty space isn't actually empty. It's full of virtual particle pairs that pop into existence and then immediately annihilate each other. This happens everywhere, all the time, but we don't notice it because the particles exist for such a short time that they don't violate conservation of energy. But near the event horizon of a black hole, Sometimes one particle of the pair falls into the black hole while the other escapes. From an outside perspective, it looks like the black hole emitted a particle. This is Hawking radiation. And because the black hole loses energy every time this happens, it slowly evaporates. Very slowly. How slowly? A black hole with the mass of the Sun would take about 1067 years to evaporate completely. That's a 1 followed by 67 zeros. The current age of the universe is about 10 plus 10 years. A solar mass black hole would take 10,000 trillion times the current age of the universe to evaporate. It would outlast every star, every galaxy, every structure in the universe. It would exist in the ultimate cold, dark void after everything else has died, and then, eventually, after incomprehensible eons, it would evaporate in a final burst of radiation and cease to exist. Black holes are patient in ways that make geological timescales look like a quick nap. But here's the truly bizarre part. Smaller black holes evaporate faster than larger ones. A black hole with the mass of a car would evaporate in about 10 to 23 seconds. A black hole with the mass of Mount Everest would evaporate in about 3 billion years, which is fast by black hole standards. And as a black hole evaporates, it gets hotter. The smaller it gets, the faster it evaporates and the more radiation it emits. In the final moments of a black hole's life, it releases a tremendous burst of energy as it evaporates away completely. Somewhere in the far future, long after the last stars have burned out, the universe will be illuminated occasionally by the final explosions of evaporating black holes. Brief flashes of light in an otherwise dead cosmos. The universe's last fireworks show. Let's talk about time, because time is fake, and I can prove it. Not fake in the sense that it doesn't exist, but fake in the sense that it's not what you think it is. Time is not a universal constant. It's not a river that flows at the same rate for everyone. It's a dimension, like space, and it's flexible. It bends and stretches depending on gravity and velocity. We've already talked about time dilation near black holes, but it happens everywhere. Right now, time is passing slightly faster for your head than for your feet, because your feet are closer to Earth's centre of mass and experience slightly stronger gravity. The difference is absurdly tiny, unmeasurable in daily life, but it's real. If you lived your entire life doing handstands, you would age very slightly faster than someone who stood upright, because your head would spend more time experiencing slightly weaker gravity. GPS satellites have to account for time dilation. They orbit at about 20,000 kilometers above Earth's surface, where gravity is weaker and time passes slightly faster than it does on the ground. If GPS satellites didn't correct for this, your phone's navigation would be off by about 10 kilometers every single day. The fact that GPS works is proof that relativity is real. Time dilation also happens with velocity. The faster you move, the slower time passes for you relative to stationary observers. This is called time dilation due to special relativity, and it's been measured countless times. If you got on a spaceship and accelerated to 99.9% the speed of light, then flew around for what felt like 1 year to you before returning to Earth, you'd find that about 22 years had passed on Earth. You'd age 1 year. Your friends and family would age 22 years. You'd return home to find that everyone you knew was decades older than when you left, while you barely aged at all. This is the twin paradox, except it's not actually a paradox. It's just what relativity predicts, and it's been confirmed experimentally with atomic clocks on airplanes. If you take an atomic clock on a flight around the world and compare it to an identical clock that stayed on the ground, the travelling clock will be very slightly behind. The difference is measured in nanoseconds, but it's measurable. Time genuinely passes slower when you're moving fast, which means that time travel to the future is not only possible, it's easy. You just have to go really fast. Astronauts on the International Space Station are time travelling into the future by tiny fractions of a second every day, because they're moving at about 28,000 kilometers per hour relative to Earth's surface. If you spent a year on the ISS, you'd age about 0.07 seconds less than someone on Earth. It's not much, but it's real. The universe said, sure, you can time travel, but only forward, and only if you're willing to go really, really fast or hang out near really, really massive objects. Let's talk about the speed of light as a speed limit, because it's not arbitrary. It's not like the universe just picked a number and said, this is as fast as you can go. The speed of light is fundamental to how space-time works. It's the speed at which causality propagates. It's the speed of information itself. Nothing with mass can reach the speed of light because as you accelerate, your mass increases. Not your weight, your mass. The faster you go, the more massive you become, and the more energy it takes to accelerate you further. To actually reach the speed of light, you'd need infinite energy, which is impossible. Light itself can travel at the speed of light because photons have no mass. They don't experience this problem. But here's the thing, from a photon's perspective, time doesn't pass. If you could experience what a photon experiences, which you can't, but if you could, the journey from the Sun to Earth would be instantaneous. 8 minutes would pass for us, but 0 time would pass for the photon. A photon emitted from a galaxy 10 billion light-years away experiences 0 time between when it leaves that galaxy and when it hits your telescope. 10 billion years pass for the universe. 0 time passes for the photon. Photons don't experience time. They exist in an eternal present, unchanging and timeless, from their own perspective. Which is deeply weird because photons are also how we experience the passage of time. We see things because photons hit our eyes. Our entire perception of time is mediated by particles that don't experience time. The universe is trolling us. Let's talk about the cosmic microwave background, because it's literally everywhere and it's the oldest thing we can see. About 380,000 years after the Big Bang, the universe cooled down enough for atoms to form. Before this, the universe was a hot, dense plasma of protons, electrons and photons, all bouncing off each other. It was opaque. Light couldn't travel freely because it would immediately hit something and scatter. But once atoms formed, photons could travel freely for the first time. The universe became transparent. Those photons have been travelling through space ever since, and we can still detect them today. That's the cosmic microwave background. It's everywhere. If you tune an old TV to a channel with no signal, about 1% of the static you see is from the cosmic microwave background. You're literally seeing the afterglow of the Big Bang on your TV. Every direction you look, in every part of the sky, there's this faint glow of microwave radiation that's been travelling toward you for 13.8 billion years. It's the oldest light in the universe. It's the echo of creation itself. And it's remarkably uniform. The cosmic microwave background has a temperature of about 2.7 Kelvin, and it's the same temperature in every direction to within about 1 part in 100,000. That's absurdly uniform. If you measured the temperature of 100,000 different points in the sky, they'd all be roughly the same temperature with only tiny variations. Those tiny variations are important though. They represent quantum fluctuations from the earliest moments of the universe, stretched out to cosmic scales by inflation. Those fluctuations became the seeds of all structure in the universe. Galaxies, galaxy clusters, superclusters, all of it traces back to tiny variations in density in the early universe that showed up as tiny variations in temperature in the cosmic microwave background. You're made of atoms that were forged in stars, but the large-scale structure that determined where those stars would form was seeded by quantum fluctuations that occurred 13.8 billion years ago and are still visible as tiny temperature differences in the cosmic microwave background. Your existence traces back to quantum noise. Let's talk about dark matter, because we have no idea what it is, and it makes up most of the universe. Here's the problem. When astronomers measure how fast galaxies are rotating, the math doesn't work. The outer parts of galaxies are moving too fast. Based on the visible mass of stars and gas, galaxies should fly apart. The gravity from the stuff we can see isn't strong enough to hold them together at the speeds they're rotating. But they don't fly apart, they stay together just fine. There are two possible explanations. Either our understanding of gravity is wrong, or there's a lot of mass in galaxies that we can't see. Most scientists believe the second option. There's invisible matter in and around galaxies that provides the extra gravity needed to hold everything together. We call it dark matter because it doesn't emit, absorb, or reflect light. It's invisible. We can only detect it through its gravitational effects. And there's a lot of it. Current estimates suggest that about 85% of the matter in the universe is dark matter. Regular matter, the stuff that makes up stars, planets, you, me, everything we can see, is only about 15% of the total matter. We're the minority. We're the weird stuff. The universe is mostly made of something we can't see, can't touch, can't detect directly, and don't understand. We've been looking for dark matter particles for decades. We've built incredibly sensitive detectors deep underground to shield them from cosmic rays, hoping to catch a dark matter particle interacting with normal matter. We haven't found anything yet. Dark matter, whatever it is, barely interacts with normal matter at all except through gravity. It's ghost matter. It passes through everything. Right now, as you listen to this, dark matter particles are passing through your body. Trillions of them. They're passing through the Earth. They're passing through the sun. They don't care. They don't interact. They just go right through everything like it isn't there. The universe is mostly made of something invisible that we don't understand, and we only know it exists because galaxies rotate wrong. Now let's talk about dark energy, which is somehow even more confusing than dark matter. In 1998, two teams of astronomers were studying distant supernovae, trying to measure how fast the universe's expansion was slowing down. Everyone assumed the expansion was slowing down because gravity should be pulling everything back together. The only question was how fast. They found that the expansion isn't slowing down, it's speeding up. The universe is expanding and the expansion is accelerating. Something is pushing space apart, working against gravity, and it's winning. We call this something dark energy because we have no idea what it is. Dark energy makes up about 68% of the total energy in the universe. Dark matter is about 27%. Regular matter, everything we can see and touch, is about 5%. We don't know what 95% of the universe is made of. We live in a universe where the vast majority of existence is completely unknown to us. Here's what really gets me about dark energy. It's a property of space itself. As space expands, you'd expect dark energy to spread out and become less dense, right? More space, same amount of dark energy. So the energy density should decrease, but it doesn't. Dark energy has a constant density. As the universe expands and creates new space, it creates new dark energy to fill that space. The total amount of dark energy in the universe is increasing over time. The universe is creating energy out of nothing. Or more accurately, space itself has an intrinsic energy density that doesn't dilute as space expands. This violates our intuitions about how energy should work, but it's what the observations show. And because dark energy is causing the expansion to accelerate, the ultimate fate of the universe is what cosmologists call the Big Freeze, or heat death. Eventually, billions of years from now, the expansion will have pushed galaxies so far apart that they'll no longer be visible to each other. The observable universe will shrink. Stars will burn out. No new stars will form because all the gas will have been used up. Black holes will evaporate. And eventually, the universe will be a cold, dark, empty void with nothing left but scattered photons and dark energy, expanding forever into a featureless infinity. That's the future of the universe, not a big crunch where everything collapses back together, not a big rip where dark energy tears everything apart, just a slow, cold fade into nothing. The universe doesn't end with a bang, it ends with an eternal whimper, alone in the dark. Happy New Year. Let's talk about the Fermi paradox, because it's one of the most unsettling questions in all of science. Here's the setup. The universe is big, incomprehensibly big. There are about 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars. Many of those stars have planets. Many of those planets are in the habitable zone where liquid water could exist. The ingredients for life, as far as we can tell, are common. Carbon, hydrogen, oxygen, nitrogen, all the building blocks. They're everywhere. Earth isn't special in terms of its composition, and the universe is old. 13.8 billion years old. The Sun is only 4.6 billion years old. There are stars much older than the Sun, and some of them have planets. Life on Earth appeared about 3.8 billion years ago, almost as soon as the planet cooled down enough to have liquid water. Intelligence took longer, but it did appear. Humans are here. We have technology. We have radio waves. We're actively trying to find other life. So here's the question. Where is everyone? If life is common, and intelligence is reasonably likely given enough time, there should be civilizations out there that are millions or billions of years older than us. They would have technology so advanced it would look like magic to us. They would have had time to colonize their entire galaxy. Even at slower than light speeds, a civilization could spread across the entire Milky Way in just a few million years, which is nothing on cosmic timescales. And yet we see no evidence of anyone, no megastructures, no artificial signals, no signs of galaxy-spanning civilizations. The universe appears to be empty, or at least it appears to be empty of other technological civilizations that want to make themselves known. This is the Fermi paradox. The universe should be teeming with life, but we don't see any. There are lots of proposed solutions. Maybe life is rarer than we think. Maybe intelligence is rarer. Maybe technological civilizations tend to destroy themselves shortly after developing advanced technology. Maybe interstellar travel is harder than we imagine. Maybe advanced civilizations deliberately hide themselves. Maybe they're here, but we don't recognize them. Maybe we're living in a simulation, and there aren't supposed to be other civilizations because it would complicate the code. Or maybe we're just early. Maybe the universe is still young enough that we're among the first civilizations to appear. Maybe in a billion years the galaxy will be full of life, but right now we're just early to the party. Or maybe we're completely alone. Maybe life is so improbable that it only happened once and we're it. Maybe intelligence is a fluke that occurred on one planet in one galaxy in an entire universe. Maybe there's nobody else out there, and there never will be. I don't know which option is more unsettling. Let's talk about the Great Filter, which is a possible explanation for the Fermi paradox, and it's absolutely terrifying. The Great Filter hypothesis says that somewhere between non-living matter and galaxy-spanning civilizations, there's a step that's extremely difficult or unlikely. A filter that almost nothing passes through. Most potential civilizations get stuck at this step and never make it further. The question is, where is the filter? If the filter is behind us, that's good news. It means the hard part was something like the origin of life, or the development of complex cells, or the evolution of intelligence. We've already passed the hard part. We made it through. The future is open. If the filter is ahead of us, that's very bad news. It means that something happens to almost every technological civilization that prevents them from spreading across the galaxy. Maybe they destroy themselves in nuclear war. Maybe they create an artificial intelligence that wipes them out. Maybe they exhaust their planet's resources. Maybe there's some technology that every civilization inevitably develops that leads to their extinction. If the filter is ahead of us, we're walking toward it right now, and we don't know what it is. And here's the really dark thought. Every time we find evidence that life might be common in the universe, that pushes the filter forward. If we find microbial life on Mars, that's bad news, because it means the origin of life isn't the filter. If we find complex life on Europa or Enceladus, that's worse news, because it means complex life isn't the filter either. The more common we find life to be, the more likely it is that the filter is ahead of us, somewhere in our future. Maybe the universe is empty because every civilization reaches a certain point and then something happens. Something consistent, something inevitable. And maybe we're approaching that point right now. Or maybe I'm wrong and the universe is full of life and we just haven't looked hard enough yet. I hope it's that one. Let's talk about vacuum decay, because we need something cheerful to balance out the existential dread. Just kidding. Vacuum decay is possibly the most terrifying concept in all of physics. Here's the idea. The universe might not be in its lowest energy state. The vacuum of space, what we think of as empty space with nothing in it, might actually be in a false vacuum state. There might be a lower energy state that the vacuum could fall into, like a ball sitting in a shallow depression on a hillside. The ball is stable, but it's not at the bottom of the hill. If something nudges it, it could roll down to a lower point. If the vacuum of space is in a false vacuum state, then at some point, somewhere in the universe, a random quantum fluctuation could cause a small region of space to drop into the true vacuum state. This would create a bubble of true vacuum expanding at the speed of light. Inside the bubble, the laws of physics would be different. Atoms couldn't exist. Matter as we know it couldn't exist. The bubble would destroy everything it touched completely and utterly, and there would be no warning because the bubble expands at the speed of light. You wouldn't see it coming. It would just hit you and erase you from existence, and once it started, there would be no stopping it. The bubble would expand forever, consuming the entire universe until everything, every galaxy, every star, every planet, every trace of existence was gone. This could happen at any moment. It could be happening right now somewhere in the universe, and we wouldn't know until the bubble reached us, billions of years from now. Or it could happen here, tomorrow, and we'd all be gone instantly. The good news is that most physicists think the vacuum is probably stable. Probably. We're pretty sure we're not in a false vacuum state, but we can't be certain, and the uncertainty is what makes it terrifying. The universe might end at any moment without warning and take everything with it. Every person, every memory, every piece of art, every scientific discovery, every thought anyone has ever had, just gone, erased at the speed of light by a bubble of different physics. Sleep tight. Let's talk about the observable universe versus the universe, because they're not the same thing and the difference matters. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's about 93 billion light years in diameter. That's what we can see in principle with perfect telescopes. But the universe, the actual full universe, is bigger than that. We don't know how much bigger. It might be infinite. It probably is infinite, based on the fact that space appears to be flat and goes on forever in every direction as far as we can tell. But we can't see beyond the observable universe, because the light from those regions hasn't had time to reach us yet. And here's the thing. Because the universe is expanding, there are regions of space that we will never see, no matter how long we wait. The light from those regions will never reach us, because the space between us and them is expanding faster than light can cross it. Those regions are beyond our cosmic horizon, permanently inaccessible. which means there could be other galaxies, other clusters, other superclusters out there, completely cut off from us. They exist, they're real. But we will never interact with them. They will never interact with us. We are cosmologically isolated from each other, forever. And if the universe is truly infinite, which it might be, then everything that can happen does happen, somewhere. There are infinite copies of you out there, in other galaxies beyond our cosmic horizon, living slightly different lives. There are versions of you who made different choices, versions who never existed, versions who are wildly successful, versions who are completely different people. Every possible variation of you exists somewhere in an infinite universe. You're simultaneously unique and one of infinite copies, depending on whether the universe is finite or infinite, and we don't know which it is. Let's talk about Boltzmann brains, because this is where physics meets philosophy and everything becomes deeply weird. Here's the thought experiment. If the universe exists for an infinite amount of time, and quantum fluctuations can create anything given enough time, then eventually, randomly, quantum fluctuations will assemble a fully formed conscious brain, just by chance. With all your memories, all your thoughts, all your perceptions, assembled from random thermal fluctuations in a dying universe. This is called a Boltzmann brain, named after Ludwig Boltzmann. And here's the disturbing part. If the universe is infinite in time, Boltzmann brains should vastly outnumber evolved brains like yours. It's far more likely for quantum fluctuations to randomly create a single brain with false memories of a past life than it is for an entire universe with stars and planets and evolution to create a brain through natural processes. Which means, statistically, if Boltzmann brains are possible, you are probably a Boltzmann brain. You probably popped into existence 1 second ago with false memories of a past life, and you'll disintegrate back into thermal noise 1 second from now. Everything you remember is fake. Everyone you know doesn't exist. The entire universe you perceive is a hallucination created by random quantum fluctuations. Most physicists think this doesn't happen because the universe isn't infinite in time, or because some aspect of physics prevents Boltzmann brains from forming. But we can't prove it. We can't rule out the possibility that you are a spontaneously assembled consciousness floating in an empty void, dreaming of a universe that doesn't exist. You're probably not a Boltzmann brain. Probably. But you can't be sure. Let's talk about quantum mechanics, because if you think relativity is weird, quantum mechanics said, "Hold my beer," and proceeded to break every intuition you have about how reality works. At the quantum scale, particles don't have definite positions until you measure them. They exist in a superposition of all possible states simultaneously. An electron doesn't have a location. It has a probability distribution. It's simultaneously everywhere it could be, with different probabilities, until you observe it, and then it collapses into having a definite location. This isn't a limitation of our knowledge. It's not that the electron has a position and we just don't know what it is until we measure it. No, the electron genuinely doesn't have a definite position until the measurement happens. The act of measurement creates the property you're measuring. This is the measurement problem, and it's been driving physicists insane for a century. The famous illustration of this is Schrödinger's cat. You put a cat in a box with a device that has a 50% chance of killing the cat. According to quantum mechanics, until you open the box and observe the cat, it's in a superposition of alive and dead simultaneously. The cat is both alive and dead. Not either alive or dead, and we don't know which. Both, at the same time. Obviously this is absurd. Cats are not both alive and dead. We know this. But the math says they should be, and the math has never been wrong when we test it. So either our interpretation of the math is wrong, or reality is deeply, fundamentally weird in ways that violate our basic intuitions about how existence works. There are lots of interpretations of quantum mechanics. The Copenhagen interpretation says that observation causes collapse and superposition is real. The many worlds interpretation says that every quantum measurement splits the universe into multiple branches, and the cat is both alive and dead, but in different universes. The pilot wave interpretation says there are hidden variables we don't understand that determine everything in advance. Quantum Bayesianism says that quantum states are about information, not reality. Nobody agrees on what quantum mechanics means, we just know that it works. Let's talk about quantum entanglement, because Einstein called it spooky action at a distance, and he was right to be spooked. When two particles are entangled, measuring one particle instantly affects the other, no matter how far apart they are. If you measure the spin of one entangled electron and find that it's spin up, the other electron instantly becomes spin down. Not is revealed to be spin down, but becomes spin down. The measurement of one particle changes the state of the other particle instantaneously across any distance. This has been tested extensively. It's real. It happens. You can entangle two particles, separate them by hundreds of kilometers, measure one, and the other instantly responds. This seems to violate relativity, because nothing is supposed to travel faster than light, including information. But entanglement doesn't violate relativity because you can't use it to send information. You can't control what result you get when you measure your particle, so you can't encode a message. The correlation is there, but it's not usable for communication. Still, it's deeply weird. Einstein hated it. He spent years trying to prove it was wrong. He failed. Entanglement is real, and we still don't fully understand what it means about the nature of reality. Are the particles connected by some kind of hidden mechanism? Do they remain fundamentally linked no matter how far apart they are? Is there some deeper layer of reality where distance doesn't matter? We don't know. Let's talk about the double slit experiment, because it's the most famous demonstration of quantum weirdness, and it still breaks my brain every time I think about it. Here's the setup. You fire electrons, one at a time, at a barrier with two slits in it. Behind the barrier, there's a screen that lights up when an electron hits it. If electrons are particles, you'd expect them to go through one slit or the other and create two bright lines on the screen. That's not what happens. Instead, you get an interference pattern with multiple bright and dark stripes. This is the kind of pattern you get with waves, not particles. It's as if each electron goes through both slits simultaneously, interferes with itself, and creates a wave pattern. Okay, fine. Maybe electrons are waves, not particles. But here's where it gets truly bizarre. If you put a detector at the slits to see which slit each electron goes through, the interference pattern disappears. Suddenly, you get two bright lines, like particles. The act of observing which slit the electron goes through changes the behavior of the electron. The electron knows whether you're watching. Observation changes reality. This isn't a metaphor, this isn't philosophy. This is what the experiments show. When you're not observing, electrons behave like waves and go through both slits. When you're observing, they behave like particles and go through one slit. Your observation determines what kind of object the electron is. Physicists have tried every possible explanation for this. Hidden variables, pilot waves, many worlds. Consciousness causes collapse. None of them are fully satisfying. The universe just does this, and we don't know why. Let's talk about quantum tunneling, because particles don't respect barriers. In classical physics, if you throw a ball at a wall, it bounces back. The ball doesn't have enough energy to go through the wall, so it doesn't. Simple. In quantum mechanics, there's a probability that the ball will tunnel through the wall and appear on the other side without ever having enough energy to pass through it. The probability is absurdly small for macroscopic objects like balls, but for particles like electrons, it happens all the time. Electrons can tunnel through barriers they shouldn't be able to cross. They just appear on the other side. No violation of energy conservation, because the tunneling happens fast enough that the energy loan from the uncertainty principle is repaid before anyone notices. The electron temporarily borrows energy, tunnels through the barrier, and gives the energy back. This is how scanning tunneling microscopes work. You bring a sharp metal tip very close to a surface, and electrons tunnel between the tip and the surface. By measuring the tunneling current, you can image individual atoms. We can literally see atoms because quantum mechanics allows particles to tunnel through barriers. It's also how the sun works. Fusion in the sun's core requires hydrogen nuclei to get close enough to fuse, but they're positively charged and they repel each other. Classically, they don't have enough energy to overcome the repulsion, but quantum tunneling allows them to occasionally tunnel through the energy barrier and fuse anyway. Without quantum tunneling, the sun wouldn't shine, stars wouldn't exist, we wouldn't exist. You exist because quantum mechanics allows particles to cheat. Let's talk about the Heisenberg uncertainty principle, because you can't know everything, and this is a fundamental law of reality, not a limitation, of measurement. The uncertainty principle says that there are pairs of properties that you cannot simultaneously know to arbitrary precision. The most famous pair is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't because our measuring tools aren't good enough. It's because the particle doesn't have a definite position and momentum simultaneously. It's forbidden by the structure of quantum mechanics. Another pair is energy and time. You can't simultaneously know the exact energy of a system and exactly when that energy was measured. This is why virtual particles can exist. They borrow energy from the vacuum for a very short time, and as long as they pay it back quickly enough, the uncertainty principle allows it. The universe has a line of credit, and particles can borrow from it as long as they don't exceed their limit. The uncertainty principle is why atoms exist. Electrons can't fall into the nucleus because if they did, we'd know their position very precisely inside the nucleus, and their momentum very precisely 0. The uncertainty principle forbids this. Electrons must have some spread in position and momentum, which keeps them in orbitals around the nucleus instead of collapsing inward. You're held together by uncertainty. Let's talk about antimatter, because for every particle there's an evil twin. Every particle has a corresponding antiparticle with the same mass but opposite charge. Electrons have positrons, protons have antiprotons, neutrons have antineutrons. When a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy, according to E/mc2. This is the most efficient energy conversion process possible. Nuclear fusion converts less than 1% of mass into energy. Matter-antimatter annihilation converts 100%. If you had 1 kilogram of matter and 1 kilogram of antimatter and brought them together, they would annihilate and release about 180 petajoules of energy. That's about 43 megatons of TNT equivalent, more than the largest nuclear bomb ever tested. Antimatter is the most efficient energy source theoretically possible, and we can make it. Particle accelerators produce antimatter all the time. The problem is that it's incredibly expensive and difficult to store. Antimatter annihilates instantly when it touches normal matter, so you have to keep it suspended in magnetic fields, and even then, it's hard to store more than a few atoms at a time. But here's the really weird thing. The Big Bang should have created equal amounts of matter and antimatter. They should have immediately annihilated each other, leaving behind a universe full of photons and nothing else. No stars, no planets, no us. And yet, here we are. The universe is made of matter, not antimatter. Why? We don't know. There's a slight asymmetry in the laws of physics that favours matter over antimatter, but we don't fully understand it. Somehow, in the early universe, slightly more matter than antimatter was created, and when everything annihilated, a small amount of matter was left over. That leftover matter is everything we see. Every atom in your body is a survivor of a cosmic annihilation event that destroyed almost all the matter and antimatter in the early universe. You're made of leftovers. Let's talk about cosmic rays, because space is shooting at us constantly. Cosmic rays are high-energy particles, mostly protons, travelling through space at nearly the speed of light. They're produced by supernovae, black holes, pulsars, and other violent cosmic events. They're constantly bombarding Earth from every direction. Most cosmic rays are stopped by Earth's atmosphere. They hit air molecules, create cascades of secondary particles, and don't reach the ground. But some do make it through. Right now, as you listen to this, cosmic ray particles are passing through your body, about 1 per second per square centimetre. You're being hit by particles that originated in a supernova explosion hundreds or thousands of light years away. Occasionally, a really high-energy cosmic ray hits Earth. These are called ultra-high-energy cosmic rays, and they have energies that shouldn't be possible. The most energetic cosmic ray ever detected, the Oh My God particle observed in 1991, had an energy of about 50 joules. That doesn't sound like much until you realise that's the energy of a baseball travelling at about 90 kilometres per hour. Except it was in a single proton. One proton with as much kinetic energy as a baseball. We don't know how cosmic rays get accelerated to these energies. The leading theory is that they're accelerated by supernova shock waves or by magnetic fields near black holes, but we can't be sure. And we don't know where the ultra-high energy ones come from because their trajectories are bent by magnetic fields in space, so we can't trace them back to their sources. Space is full of high-energy particles moving at relativistic speeds, and we're just sitting here in the firing range, protected only by a thin layer of atmosphere. Let's talk about solar flares and coronal mass ejections, because the sun occasionally tries to kill us. The sun has a magnetic field, and it's complicated and messy because the sun is made of plasma, and different parts of the sun rotate at different speeds. The magnetic field gets twisted and tangled, and occasionally it snaps. When it does, it releases enormous amounts of energy in the form of solar flares and coronal mass ejections. A solar flare is a burst of radiation across the electromagnetic spectrum, from radio waves to gamma rays. A large flare can release as much energy as 1 billion hydrogen bombs. The radiation travels at the speed of light, so if a flare happens, we find out about it 8 minutes later when the radiation hits Earth. A coronal mass ejection is a massive eruption of plasma from the sun's corona. Billions of tons of charged particles are thrown into space at millions of kilometers per hour. If a CME hits Earth, it can cause geomagnetic storms that disrupt satellites, power grids, and communication systems. In 1859, a massive solar storm called the Carrington event hit Earth. It was the most powerful geomagnetic storm ever recorded. Telegraph systems worldwide failed. Some operators received electric shocks. Telegraph paper caught fire. Auroras were visible as far south as the Caribbean. And this happened in 1859, when we barely had any technology. If a Carrington event-level storm hit Earth today, it would be catastrophic. Satellites would fail, GPS would stop working, power grids would overload and shut down, communication systems would fail. Some estimates suggest that a Carrington-level event today could cause trillions of dollars in damage and leave parts of the world without power for months. and it could happen at any time. The sun is always active. Solar flares and CMEs happen regularly. We just got lucky that none of them have been pointed directly at Earth recently, but we will get hit by another major solar storm eventually. It's not a matter of if, but when. This sun is a giant nuclear furnace, and occasionally it burps in our direction. Let me talk to you about the Voyager spacecraft, because they're the farthest human-made objects from Earth, and they're still sending back data. Voyager 1 and Voyager 2 were launched in 1977 to study Jupiter, Saturn, Uranus, and Neptune. They completed their primary missions in the late 1980s and early 1990s, and then they just kept going. They're now in interstellar space beyond the influence of the sun's solar wind, travelling through the void between stars. Voyager 1 is about 24 billion kilometres from Earth. Voyager 2 is about 20 billion kilometres away. They're moving at about 17 kilometres per second and 15 kilometres per second respectively, relative to the Sun. They'll keep moving forever, or at least until they eventually get pulled into the gravity well of another star, which won't happen for tens of thousands of years at minimum, and they're still working. Both Voyagers are still powered by radioisotope thermoelectric generators that convert heat from radioactive decay into electricity. They're producing less power now than they did at launch, because the radioactive material is decaying, but they're still producing enough to run some of their instruments. NASA has been shutting down non-essential systems one by one to conserve power, but the spacecraft are still sending back data about the interstellar medium. It takes about 22 hours for a signal from Voyager 1 to reach Earth, travelling at the speed of light. When NASA sends a command to Voyager 1, they wait 22 hours for the spacecraft to receive it, and then another 22 hours for the confirmation signal to come back. That's a 44-hour round-trip communication delay for an object that hasn't even left our galaxy yet. Both Voyagers carry a golden record, a phonograph record containing sounds and images from Earth, music, greetings in multiple languages, pictures of humans and our world. The idea was that if aliens ever find one of the Voyagers, they'd have some information about who made it. The records are made of gold-plated copper and are designed to last billions of years. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. It won't be captured by the star's gravity. It'll just drift past, continuing its journey through the galaxy. In a few 100 million years, both Voyagers will have completed one full orbit around the Milky Way. They'll still be travelling, silent and dead, their power sources long depleted, but still carrying those golden records. Their messages in bottles, thrown into an ocean so vast that they'll probably never be found. But they're out there. We sent them. 2 tiny machines built by humans travelling through interstellar space, carrying information about our existence. We're a species that builds things and then sends them into the void. Let's talk about how many planets there probably are. The Milky Way contains somewhere between 100 and 400 billion stars. That's our current best estimate. Let's call it 200 billion to be conservative. Recent exoplanet surveys, especially from the Kepler Space Telescope, suggest that most stars have planets. Not all, but most. Let's say 1 planet per star on average. That's 200 billion planets in the Milky Way alone. And remember, there are about 2 trillion galaxies in the observable universe. If each galaxy has roughly as many planets as the Milky Way, that's about 400 sextillion planets in the observable universe. 400 sextillion? That's 400,000 planets. And that's just in the observable universe. The full universe is larger, possibly infinite. There are more planets than there are grains of sand on all the beaches on Earth. More planets than there are cells in your body. More planets than there are seconds in 1 trillion years. and we've only confirmed the existence of about 5,000 exoplanets. We've looked at a tiny, tiny fraction of the sky, and we found thousands. The universe is absolutely full of planets, rocky planets, gas giants, ice giants, super-Earths, mini-Neptunes, planets orbiting red dwarfs, yellow dwarfs, white dwarfs, binary stars, planets so close to their stars that their surfaces are molten, planets so far from their stars that they're frozen solid, rogue planets with no star at all. The universe is not empty. It's crowded with worlds, most of which we'll never see, never name, never know exist. Somewhere out there, orbiting a star we've never observed, in a galaxy we'll never see, there's probably a planet with oceans and continents and weather and maybe even life. And it has no idea we exist. And we have no idea it exists. Two worlds separated by distances so vast that light itself takes billions of years to cross them, completely isolated from each other forever. Let's talk about the Oort cloud, because the solar system is much bigger than you think. When people picture the solar system, they usually think of the Sun, the 8 planets, maybe the asteroid belt and the Kuiper belt where Pluto lives. That's the inner solar system, but the solar system doesn't end there. Far beyond Neptune, beyond the Kuiper belt, there's a vast spherical cloud of icy objects called the Oort cloud. It starts at about 2,000 astronomical units from the Sun, 1 AU being the distance from Earth to the Sun, and extends out to about 100,000 AU. For reference, Neptune is about 30 AU from the Sun. The Oort cloud is thousands of times farther out. We've never actually seen the Oort cloud directly. We infer its existence from the orbits of long-period comets, which seem to come from a region far beyond the planets. These comets have orbital periods of hundreds or thousands or even millions of years, and they come from all directions, suggesting a spherical distribution of objects surrounding the solar system. The Oort cloud probably contains trillions of objects, most of them small icy bodies. The total mass is estimated to be a few times the mass of Earth, spread out over an absolutely enormous volume of space. And it's the source of most of the comets that occasionally fall into the inner solar system and put on a show in our skies. Here's the thing, the outer edge of the Oort cloud is about halfway to the nearest star. Objects in the outer Oort cloud are so loosely bound to the Sun that passing stars can perturb their orbits. When another star passes within a few light years of the Sun, which happens every few million years, it can gravitationally nudge Oort cloud objects, sending some of them falling toward the inner solar system and ejecting others into interstellar space. The solar system is constantly losing Oort cloud objects to passing stars, and it's probably also capturing objects from other stars' Oort clouds. There are probably objects in our Oort cloud that originated around other stars. We've stolen comets from our neighbours. The Sun's gravitational influence extends halfway to the nearest star, which means the nearest star's influence extends halfway here. The Oort clouds of neighbouring stars probably overlap. The solar system doesn't have a sharp boundary. It gradually fades out into the space between stars. Let's talk about how hard it is to get to space. Earth's escape velocity is about 11.2 kilometers per second. That's how fast you need to go to escape Earth's gravity completely. For comparison, a bullet from a rifle travels at about 1 kilometer per second. You need to go 11 times faster than a bullet to leave Earth. Getting to orbit is slightly easier because you don't have to escape Earth's gravity completely. You just have to go fast enough that you keep missing Earth as you fall. The International's space station orbits at about 400 kilometers altitude and travels at about 7.7 kilometers per second. But you can't just point a rocket straight up and accelerate to orbital velocity, because you'd burn up in the atmosphere from air resistance. Instead, rockets launch straight up to get out of the thickest part of the atmosphere, and then they gradually pitch over and accelerate horizontally. Most of the energy in a rocket launch goes into achieving horizontal velocity, not altitude. Getting to space is easy, getting to orbit is hard. And here's the problem: rockets are terrible. The rocket equation, derived by Konstantin Tsiolkovsky, says that the change in velocity you can achieve depends on the exhaust velocity of your rocket and the ratio of your initial mass to your final mass. To go faster, you need to carry more fuel. But carrying more fuel means you're heavier, which means you need even more fuel to accelerate that extra weight, which makes you heavier still, which means you need even more fuel. It's exponential. If you want to go twice as fast, you don't need twice as much fuel. You need exponentially more. This is why rockets are mostly fuel. The Saturn V rocket that took astronauts to the moon was about 85% fuel by mass. The Space Shuttle was about 85% fuel. SpaceX's Starship is about 90% fuel. And you can't just add more fuel indefinitely, because eventually the rocket becomes so heavy that it can't lift itself. There's a maximum delta V you can achieve with chemical rockets, and it's not enough to make interstellar travel practical. Even getting to Mars takes months and requires enormous amounts of fuel. This is the tyranny of the rocket equation. We're stuck on Earth not because we lack the technology to build spaceships, but because physics makes it incredibly difficult and expensive to get off the planet. We live at the bottom of a gravity well, and climbing out takes enormous amounts of energy. Let's talk about orbital mechanics, because space travel is not intuitive. If you're in orbit and you want to catch up to something ahead of you, you don't speed up by accelerating forward. That would raise your orbit and make you go slower. Instead, you slow down, which lowers your orbit, which makes you go faster and you catch up. Then you speed up again to raise your orbit back to where you want to be. To go faster, you slow down. To slow down, you speed up. Orbital mechanics is deeply counterintuitive. There's also the Oberth effect, which says that rocket burns are more effective when you're moving faster. If you want to change your trajectory, you get more bang for your buck by burning your rockets when you're at the highest velocity, which is usually at periapsis, the closest point to the body you're orbiting. This is why interplanetary missions often involve complex gravity assists, where the spacecraft flies close to a planet and uses the planet's gravity to change its velocity. The spacecraft doesn't use any fuel for this. It just falls toward the planet, swings around it, and gets flung out in a new direction at a higher speed. NASA's Voyager missions used gravity assists at Jupiter and Saturn to reach Uranus and Neptune. Without gravity assists, they never could have made it. Space travel is basically a game of pool played with gravity and orbital mechanics. You line up your shots, use gravity to bounce off planets, and hope you calculated everything correctly. And if you screw up, you don't get a do-over, you're on a trajectory, and unless you have enough fuel to correct it, that's where you're going. Space missions require insane precision. If you're launching to Mars and you miss by a few kilometers per second in velocity, you don't get to Mars. You go somewhere else, and maybe you never come back. Let's talk about Lagrange points, because there are places in space where you can just park. When you have two massive bodies orbiting each other, like Earth and the Moon or Earth and the Sun, their gravitational fields create 5 special points called Lagrange points, where the forces balance out in interesting ways. If you put an object at one of these points, it'll stay there, more or less, without needing to use fuel to maintain its position. The James Webb Space Telescope is at L2, the second Lagrange point of the Sun-Earth system, about 1.5 million kilometers from Earth on the side away from the Sun. At L2, Earth and the Sun are always in the same direction, which means Webb can keep its sunshield pointed at both of them, while observing deep space in the opposite direction. It's a great spot for a space telescope. L4 and L5 are particularly stable. Objects placed at these points will tend to stay there even if perturbed slightly. There are actually asteroids trapped at Jupiter's L4 and L5 points, called Trojan asteroids. Some scientists have proposed building space stations at Earth's L4 and L5 points because they're gravitationally stable and you wouldn't need to spend much fuel keeping them there. Lagrange points are basically parking spaces in orbit. The universe gives us these little pockets of stability where we can put things and they'll just stay there. Let's talk about space junk because we've accidentally surrounded Earth with a cloud of debris and it's becoming a problem. Every time we launch a satellite, every time a rocket stage separates, every time something in orbit breaks apart or explodes, we create debris. Tiny fragments of metal and paint travelling at orbital velocities. And orbital velocity is fast, about 7.7 kilometers per second in low Earth orbit. At that speed, even a fleck of paint can damage a spacecraft. A screw can punch through a satellite. A defunct satellite hitting an active one would be catastrophic. There are currently over 30,000 tracked objects in orbit larger than 10 centimeters. There are probably hundreds of thousands of objects between 1 and 10 centimeters that we can't track. And there are millions of smaller fragments. And it's getting worse. The more stuff we put in orbit, the higher the chances of collisions. And every collision creates more debris, which increases the chances of more collisions. This is called Kessler syndrome, a cascade of collisions that could make low Earth orbit unusable for decades or longer. In 2009, an inactive Russian satellite collided with an active American communications satellite, creating thousands of pieces of debris. In 2007, China destroyed one of its own satellites in a weapons test, creating thousands more pieces of debris. These events contributed significantly to the orbital debris problem. We're filling the space around Earth with trash, and we don't have a good way to clean it up. Some proposals involve using lasers to nudge debris into lower orbits where it'll burn up in the atmosphere, or launching spacecraft with nets or harpoons to capture large debris. But these are expensive and technically challenging. We might be in the process of accidentally locking ourselves out of space by surrounding our planet with a cloud of hypervelocity debris. Let's talk about the Apollo program, because we went to the moon 50 years ago, and it's still one of the most impressive things humans have ever done. The moon is about 384 to 400 kilometers away. That's far. Really far. The International Space Station is about 400 kilometers up. The moon is almost 1,000 times farther away, and we sent people there, multiple times, and brought them back. Apollo 11 launched on July 16th, 1969, landed on the moon on July 20th, and returned to Earth on July 24th. The whole mission took 8 days. Neil Armstrong and Buzz Aldrin walked on the moon for about 2.5 hours. Michael Collins orbited the moon in the command module, alone, while his crewmates were on the surface. The technology they used was absurdly primitive by modern standards. The Apollo guidance computer had 64 kilobytes of memory and operated at 0.04 MHz. Your phone is millions of times more powerful. They navigated to the moon using 1960s computers, and they did it successfully 6 times. 12 astronauts walked on the moon between 1969 and 1972. And then we stopped. We haven't been back since 1972. Not because we lost the technology, but because we lost the political will and the funding. The Apollo program cost about $25 billion in 1960s dollars, which is about $280 billion in today's money. It was expensive. And after we beat the Soviets to the moon, there was no longer a geopolitical reason to keep going. So we stopped. We built the Skylab space station. We flew the space shuttle for 30 years. We built the International Space Station. But we didn't go back to the moon. Now, more than 50 years later, we're planning to go back. NASA's Artemis program is supposed to land astronauts on the moon again in the next few years. But it's taking longer and costing more than Apollo did, even accounting for inflation. We're struggling to do something we did 50 years ago with computers less powerful than a graphing calculator. Sometimes progress isn't linear. Let's talk about the speed of sound in space, because it's zero. Sound doesn't travel in a vacuum. Sound is a pressure wave. It requires a medium to propagate through. Air, water, solid materials, anything with atoms that can vibrate and bump into each other. In space, there's no medium. The density of interstellar space is about 1 atom per cubic centimetre. That's not enough to carry sound. In science fiction movies, spaceships make roaring sounds as they fly past the camera. Explosions are loud and dramatic. In reality, it would be silent. No sound at all. Just silence. If you were floating in space and a spaceship exploded nearby, you wouldn't hear anything. You'd see a flash of light, and then you'd see debris silently expanding outward, and then the shockwave would hit you, but you wouldn't hear it, because there's no air to carry the sound. Space is silent. There is a caveat though. In the dense gas clouds where stars form, sound can travel. The density is high enough that pressure waves can propagate, and scientists have measured sound waves in these clouds. In 2003, NASA released a recording of sound waves from a black hole in the Perseus galaxy cluster. Well, not a recording exactly. They measured pressure waves in the hot gas surrounding the black hole and translated them into sound waves at frequencies we can hear. The black hole is producing a B-flat, 57 octaves below middle C. It's been producing this note for about 2 billion years. It's the deepest note in the universe. So space isn't completely silent, but it's mostly silent, unless you're hanging out in an intergalactic gas cloud listening to a black hole hum. Alright, let's shift gears. We've been sprinting through the weird and wonderful universe at maximum velocity for a while now, and if you're still here, still awake, you've earned a slightly slower pace. Not boring, never boring, but let's call it meditative. We're transitioning into the part of this journey where the facts are still fascinating, but the delivery becomes a little gentler. The hooks are still there, but they're softer now. We're settling in. Think of this as the second act of our cosmic exploration. The universe isn't getting less interesting, but we're going to take our time with it now. We're going to let concepts breathe a little. Let's talk about how old the universe actually is and what that means for everything. The universe is approximately 13.8 billion years old. This isn't a guess. We can measure it using multiple independent methods, and they all agree to within about 1%. We measure the expansion rate of the universe, the temperature of the cosmic microwave background, the ages of the oldest stars, and they all tell us the same story. 13.8 billion years. That's a long time. But let's put it in perspective. If the universe were 1 year old, with the Big Bang happening at midnight on January 1st, the first stars would have formed around January 20th. The Milky Way would have formed sometime in late February or early March. The solar system would have formed on September 1st. The first multicellular life on Earth would appear on December 15th. Dinosaurs would evolve on December 25th and go extinct on December 30th. Humans would appear in the final hour of December 31st. All of recorded human history would happen in the last 10 seconds before midnight. The universe is old, almost incomprehensibly old, and we're so young in comparison. The oldest stars in the universe are about 13.5 billion years old. They formed just a few 100 million years after the Big Bang. They're called population 3 stars, and we've never actually seen one. They should exist, but they're incredibly rare and very dim because they've been burning for so long. These stars formed from hydrogen and helium alone, because nothing else existed yet. No carbon, no oxygen, no iron. Just the two simplest elements. Later stars, like our Sun, formed from material that included heavier elements created in earlier generations of stars. We're second generation at minimum, maybe third or fourth. The atoms in your body were created in stars that lived and died billions of years ago, and then those atoms were incorporated into the cloud of gas and dust that collapse to form the Sun and the solar system. You're made of recycled star material. Everyone is. Every atom heavier than helium in your body was forged in a star or in a supernova explosion. You are star stuff. Literally. Let's talk about how the universe will end. We've already mentioned the big freeze, but let's go into detail about what that actually means. The universe is expanding, and the expansion is accelerating because of dark energy. Eventually, billions of years from now, the expansion will have carried galaxies so far apart that they'll no longer be gravitationally bound to each other. Galaxy clusters will dissolve. Galaxies will drift away from each other into isolation. Within each galaxy, stars will continue to form for a while, but eventually all the gas will be used up. No more star formation. The stars that exist will continue burning until they run out of fuel. The largest stars will explode as supernovae or collapse into black holes. Mid-sized stars like the Sun will expand into red giants, then shed their outer layers and become white dwarfs. The smallest stars, red dwarfs, will continue burning for trillions of years. But eventually even the red dwarfs will burn out. The last stars will flicker and die. The universe will be dark except for the faint glow of white dwarfs and neutron stars slowly cooling down. White dwarfs will eventually become black dwarfs, cold dead stars that no longer emit light. Neutron stars will cool as well. Black holes will evaporate through Hawking radiation. But this will take an unimaginably long time. A black hole with the mass of the Sun will take 10 to 67 years to evaporate. Supermassive black holes will take even longer, maybe 1,000 years or more. But eventually even the black holes will evaporate, and then the universe will be empty, just photons and neutrinos and dark energy, spreading apart forever, getting colder and emptier until nothing remains but a nearly infinite expanse of nearly empty space at nearly absolute zero temperature. This is the heat death of the universe. Maximum entropy. No more structure. No more complexity. No more change. Just an unchanging, eternal void. The universe doesn't end with a bang. It ends with a whisper, fading into silence over timescales so long that the entire history of stars and galaxies is just a brief flicker at the beginning. But that won't happen for a very long time. Trillions of years, at minimum. We have time. Let's talk about the cosmic calendar, a way of conceptualizing the history of the universe by compressing it into a single year. Carl Sagan popularized this idea. If the Big Bang happened at midnight on January 1st, and the present moment is midnight on December 31st, you can map all of cosmic history onto a calendar. The first stars ignite on January 10th. The Milky Way forms on February 11th. The solar system and Earth form on September 1st. Life appears on Earth on September 21st. Photosynthesis evolves on October 2nd. The atmosphere becomes oxygen-rich on December 1st. The first multicellular life appears on December 14th. The Cambrian explosion, when complex life diversified rapidly, happens on December 17th. Dinosaurs appear on December 25th, Christmas Day. They dominate the planet for several days. Then, on December 30th, at 6 AM, an asteroid hits Earth and the dinosaurs go extinct. Humans evolve very late. Homo sapiens appears at 11:52 PM on December 31st, 8 minutes before midnight. Agriculture is invented at 11:59:20. The pyramids are built at 11:59:46. The Roman Empire rises and falls in the last few seconds. The entire Renaissance happens in the last half second. Modern human civilization, everything we've built, all of recorded history, happens in the final moments of the year. This is how young we are. How recent. The universe existed for 13.8 billion years before humans showed up, and we've only been around for about 300,000 years. We've been doing science for maybe 500 years. We've had telescopes for 400 years. We've understood the true nature of stars for less than 200 years. We're infants on a cosmic scale. We just got here. Let's talk about the anthropic principle, which is either profound or trivial depending on how you interpret it. The anthropic principle observes that the universe appears to be fine-tuned for life. The fundamental constants of physics, things like the strength of gravity, the mass of the electron, the speed of light, all seem to be set to values that allow for the existence of stars, planets, chemistry, and ultimately life. If any of these constants were even slightly different, the universe would be very different, possibly unable to support life at all. For example, if the strong nuclear force was slightly weaker, atomic nuclei wouldn't hold together, and there would be no atoms heavier than hydrogen. If it were slightly stronger, hydrogen would fuse too easily and stars would burn out almost instantly. If gravity were stronger, stars would collapse into black holes. If it were weaker, stars wouldn't form at all. The universe seems to be balanced on a knife's edge between too much and too little, and somehow it's landed in a range where complex structures can exist. There are several possible explanations for this. One is the multiverse hypothesis. There are countless universes with different physical constants, and we happen to live in one where the constants allow for life because obviously we couldn't exist in a universe where life was impossible. We're here because the conditions allow us to be here. It's selection bias on a cosmic scale. Another interpretation is that the universe actually is fine-tuned, intentionally, by something or someone. This edges into philosophical and religious territory, and science doesn't have much to say about it. A third interpretation is that we're wrong about some of our assumptions, and the apparent fine-tuning is an illusion caused by our incomplete understanding of physics. Personally, I find the multiverse explanation compelling, but we have no way to test it. Other universes, if they exist, are by definition beyond our cosmic horizon and can never be observed. It's a hypothesis that can't be proven or disproven, which makes some scientists uncomfortable. But it's interesting to think about. The fact that we exist at all might be evidence that there are countless other universes where nothing interesting happens, and we just happen to be in one of the rare ones where things worked out. Let's talk about the scale of atoms, because people know atoms are small, but they don't know how small. An atom is about 10 meters across. That's 1 meters. 1/10,000,000th of a meter. If you scaled an atom up to the size of a football stadium, the nucleus would be the size of a marble sitting at the centre of the field. The electrons would be tiny dots orbiting somewhere in the upper seats. Everything in between would be empty space. Atoms are almost entirely empty space. You're almost entirely empty space. The chair you're sitting on is almost entirely empty space. The reason you don't fall through the chair is because the electrons in your atoms and the electrons in the chair's atoms repel each other through electromagnetic forces. You're not really touching the chair. You're being held up by electromagnetic repulsion between clouds of electrons that are mostly empty space. Touch is an illusion. Contact is an illusion. Solidity is an illusion created by electromagnetic forces between clouds of probability. Now let's go smaller. The nucleus of an atom is about 10^15 meters across, 100,000 times smaller than the atom itself, and the protons and neutrons in the nucleus are made of quarks, which are, well, we don't know how big quarks are. They might be point particles with no physical size at all. As far as we can tell with our current experiments, quarks are smaller than 10^19 meters, but they might be genuinely zero-dimensional points. The universe contains structures on every imaginable scale, from the genuinely smallest things we know of, quarks and electrons, to the largest structures we know of, galaxy superclusters and cosmic filaments billions of light years across, and we exist somewhere in the middle, able to study both extremes. Let's talk about what happens when stars die. because it depends on their mass, and the outcomes are very different. Small stars, those with less than about half the mass of the Sun, burn slowly and can last for trillions of years. These are red dwarfs, and none of them have died yet because the universe isn't old enough. The smallest red dwarfs will outlast everything else. They'll be the last stars shining in a dying universe. Mid-sized stars like the Sun burn faster. The Sun will last about 10 billion years total. It's currently about 4.6 billion years old, so it's middle-aged. In another 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This will cause it to expand into a red giant. It'll grow so large that it will likely engulf Mercury and Venus and possibly Earth, though Earth might survive in a very tight, very hot orbit. Eventually the Sun will shed its outer layers in a planetary nebula, leaving behind its core as a white dwarf. The white dwarf will slowly cool over billions of years, fading from white to yellow to red to eventually black. Though this will take longer than the current age of the universe. Large stars, those with more than about 8 times the mass of the Sun, have more dramatic deaths. They burn hot and fast, fusing heavier and heavier elements in their cores. Hydrogen fuses to helium, helium fuses to carbon and oxygen, carbon and oxygen fuse to neon, magnesium, silicon. Silicon fuses to iron, and then fusion stops. Iron is the most stable nucleus. Fusing iron doesn't release energy, it requires energy. Once the core of a massive star turns to iron, there's no more fuel. The core can no longer support itself against gravity. The core collapses. In less than a second, the core of a star the size of Earth compresses to about 20 kilometers across. The collapse releases an enormous amount of gravitational potential energy, most of it in the form of neutrinos. The outer layers of the star, no longer supported by pressure from the core, fall inward and then bounce off the collapsing core, creating a shock wave that tears the star apart. This is a supernova. For a few weeks, the exploding star can outshine an entire galaxy. It releases more energy in those few weeks than the Sun will release in its entire 10 billion year lifetime, and what's left behind depends on the mass of the core. If the core is less than about 3 times the mass of the Sun, it becomes a neutron star. If the core is more massive than that, nothing can stop the collapse. It becomes a black hole. Massive stars create their own graves. Let's talk about what it would be like to fall into the Sun. You can't, obviously. You'd die long before you got there from heat and radiation. But let's imagine you're invulnerable and you start falling toward the Sun from Earth's orbit. It would take about 65 days to fall into the Sun if you started from rest at Earth's distance. You'd accelerate as you fell, pulled by the Sun's gravity, reaching speeds of hundreds of kilometers per second by the time you arrived. As you got closer, the Sun would grow larger and brighter. From Earth, the Sun has an angular diameter of about half a degree. It looks small, but as you fell toward it, it would grow and grow until it filled your entire field of vision. You'd be falling toward a wall of nuclear fire. The temperature would increase. Earth orbits at a distance where the temperature is about 300 Kelvin, comfortable for life. But closer to the Sun, the temperature rises. At Mercury's orbit, it's about 600 Kelvin. At Venus's orbit, about 500 Kelvin. As you continued falling, the temperature would reach thousands of Kelvin, then tens of thousands. By the time you reached the Sun's surface, you'd be moving at about 600 kilometers per second. The temperature would be about 5,800 Kelvin, and you'd plunge into the photosphere, the visible surface of the Sun. Except it's not really a surface. The Sun is made of gas. The photosphere is just the layer where the gas becomes opaque enough that we can't see deeper. You'd pass through it and continue falling into the Sun's interior. The temperature would continue to increase. Thousands of Kelvin, tens of thousands, hundreds of thousands. the pressure would increase as well, crushing you from all sides. Eventually you'd reach the core, about 200,000 kilometers down, where the temperature is about 15 million Kelvin and the pressure is about 250 billion times Earth's atmospheric pressure. This is where fusion happens. Hydrogen nuclei slam together and fuse into helium, releasing energy, and you'd be there in the center of the sun, experiencing conditions that don't exist anywhere else in the solar system, except in other stars. Of course, you'd have been vaporized long before you got there. But it's interesting to think about. Let's talk about the concept of a light year and what it really means. A light year is the distance light travels in 1 year. Light moves at 290,792,458 meters per second, which is about 300,000 kilometers per second. In 1 year, light travels about 9.46 trillion kilometers. That's 1 light year. Alpha Centauri, the nearest star system, is 4.37 light years away. That means the light we see from Alpha Centauri left that star 4.37 years ago. When you look at Alpha Centauri, you're seeing it as it was 4.37 years in the past. Sirius, the brightest star in the night sky, is 8.6 light years away. The light you see from Sirius tonight left the star in 2016. Betelgeuse, the red supergiant in Orion, is about 550 light years away. The light from Betelgeuse that reaches your eyes tonight left that star in the year 1474. Leonardo da Vinci was alive. The printing press has just been invented. Columbus wouldn't sail to the Americas for another 18 years. The Andromeda Galaxy is 2.5 million light years away. The light from Andromeda that you see tonight left that galaxy 2.5 million years ago, when the first Homo habilis were using stone tools on Earth. The farther you look into space, the farther back in time you're looking. The universe is a time machine. Every photon that hits your eye is a messenger from the past. The most distant galaxies we've observed are about 13.4 billion light years away. We're seeing them as they were 13.4 billion years ago, less than 400 million years after the Big Bang. Those galaxies look young because they are young. We're seeing them at the beginning of their lives. And here's the strange thing. Those galaxies don't exist anymore, at least not in the form we see them. In the 13.4 billion years since the light we're seeing left those galaxies, they've evolved, changed, merged with other galaxies, maybe been torn apart by collisions. The galaxies we see in the deepest images from the James Webb Space Telescope don't look like that anymore. We're seeing ghosts, images from the distant past of objects that have long since changed beyond recognition. Every observation in astronomy is archaeology. We're always looking at the past. Let's talk about redshift and blue shift, because they're how we know the universe is expanding. When an object is moving away from you, the light from that object gets stretched to longer wavelengths. Visible light shifts toward the red end of the spectrum. This is called redshift. It's the same phenomenon as the Doppler effect for sound. A siren sounds higher pitched when it's moving toward you, and lower pitched when it's moving away. Light does the same thing. When astronomers look at distant galaxies, they see that the light from those galaxies is redshifted. The farther away the galaxy is, the more redshifted its light is. This means distant galaxies are moving away from us, and the farther away they are, the faster they're moving away. This is how we know the universe is expanding. Every distant galaxy is moving away from us, and the more distant they are, the faster they're receding. It's not that we're at the center of the universe and everything is moving away from us specifically. It's that space itself is expanding, and every point in space is moving away from every other point. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move apart from each other, not because the dots are moving across the surface, but because the surface itself is expanding. That's what's happening to the universe. Space itself is stretching, and galaxies are carried along with it. The most distant galaxies we can see are moving away from us at speeds that exceed the speed of light. Not because they're travelling through space faster than light, but because the space between us and them is expanding so fast that the distance is increasing faster than light can cross it. This doesn't violate relativity because the speed limit only applies to objects moving through space. It doesn't apply to the expansion of space itself. Space can expand as fast as it wants, and it does. Let's talk about what would happen if the Earth suddenly stopped spinning. The Earth rotates once every 24 hours. At the equator, the surface is moving at about 1,170 kilometers per hour. That's fast. You don't feel it because everything around you is moving at the same speed, but you're travelling at over 1,600 kilometers per hour right now, just due to Earth's rotation. If the Earth suddenly stopped spinning, you wouldn't. You'd continue moving at 1,670 kilometers per hour in the direction you were going. Everything not securely attached to the Earth's surface, including you, the oceans, the atmosphere, and everything else, would continue moving at that speed while the ground stopped. It would be catastrophic. Everything would be flung eastward at supersonic speeds. The atmosphere would continue moving, creating winds faster than any hurricane. The oceans would slosh out of their basins and sweep across the continents. Buildings would collapse, mountains would crumble from the stress. It would be the end of everything on the surface, and that's just the immediate effect. If Earth stopped rotating but continued orbiting the Sun, one side of the planet would face the Sun constantly, while the other side faced away. The day side would bake, the night side would freeze. The temperature difference would create violent storms as air rushed from the hot side to the cold side and back. Eventually, assuming anything survived, life might adapt, but it would be a very different Earth. Of course, the Earth isn't going to suddenly stop spinning. There's no mechanism that could do that. The Earth's rotation is gradually slowing down due to tidal forces from the Moon, but this happens so slowly that a day lengthens by about 1.7 milliseconds per century. In a few billion years, Earth's day will be longer, maybe 25 or 30 hours, but it's not going to stop. Let's talk about the Moon and how it affects Earth. The Moon causes tides. Most people know this. The Moon's gravity pulls on the Earth, and because water can flow, it creates bulges of water on the side of Earth facing the Moon and on the opposite side. As Earth rotates, these bulges move around the planet, creating high and low tides. But the Moon does more than cause tides. The gravitational interaction between Earth and the Moon is gradually slowing Earth's rotation. The energy lost by Earth's rotation is transferred to the Moon's orbit, causing the Moon to slowly move away from Earth. The Moon is currently moving away at about 3.8 centimeters per year. Billions of years ago, the Moon was much closer to Earth. Days were shorter, maybe 18 or 20 hours. Tides were much stronger. The Moon appeared much larger in the sky. As the Moon moves away, days get longer and tides get weaker. Eventually, in a few billion years, the Moon will be so far away that Earth's rotation and the Moon's orbit will be tidally locked. Earth will rotate once per lunar orbit, so the same side of Earth will always face the Moon, just like the same side of the Moon always faces Earth now. A day will be as long as a month. But this won't happen for billions of years, and by that time the Sun will have expanded into a red giant and probably destroyed both Earth and the Moon, so it's not really a concern. The Moon also stabilizes Earth's axial tilt. Earth's axis is tilted about 23.5 degrees relative to its orbital plane, and this tilt is what causes seasons. The Moon's gravitational influence keeps this tilt stable. Without the Moon, Earth's axial tilt would vary chaotically over millions of years. The Moon also stabilizes Earth's axial tilt. Earth's axis is tilted about 23.5 degrees relative to its orbital plane, and this tilt is what causes seasons. The moon's gravitational influence keeps this tilt stable. Without the moon, Earth's axial tilt would vary chaotically over millions of years, swinging from nearly 0 degrees to maybe 85 degrees. This would cause wild climate variations. Sometimes Earth would have almost no seasons. Sometimes the poles would point nearly at the sun, causing extreme seasonal variations. Mars doesn't have a large moon, and its axial tilt varies significantly over millions of years. This has likely contributed to Mars losing its atmosphere and becoming the cold, dry planet it is today. Earth got lucky. We have a large moon that stabilizes our climate and makes long-term biological evolution possible. The moon might be one of the reasons life was able to evolve and thrive on Earth. Let's talk about eclipses, because they're one of the most remarkable coincidences in the solar system. The Sun is about 400 times larger than the Moon. The Sun is also about 400 times farther away from Earth than the Moon. This means that from Earth's perspective, the Sun and Moon appear to be almost exactly the same size in the sky. This is why we can have total solar eclipses. The Moon is just barely large enough to completely cover the Sun's disk when it passes in front of it. During a total solar eclipse, the Moon blocks out the Sun's bright photosphere, allowing us to see the Sun's corona, the faint outer atmosphere that's normally invisible due to the brightness of the photosphere. This is an incredible coincidence. There's no physical reason why the Sun and Moon should appear the same size from Earth. It's just luck. And it won't last forever. The Moon is slowly moving away from Earth, and in a few 100 million years, it will be too far away to completely cover the Sun. Total solar eclipses will no longer be possible. We live in a brief window of cosmic history when total solar eclipses are possible. Humans are lucky enough to live at a time when we can see them. Let's talk about the formation of the Moon, because the leading theory involves a collision so violent it's hard to imagine. About 4.5 billion years ago, shortly after Earth formed, a Mars-sized object called Theia collided with the early Earth. The impact was catastrophic. Theia was destroyed. A significant portion of Earth's mantle was vaporized and ejected into space. The debris from the collision formed a ring around Earth, and over time, this debris coalesced into the Moon. This explains several things about the Moon. It explains why the Moon is large relative to Earth compared to most other planet-moon systems. It explains why the Moon's composition is similar to Earth's mantle but different from Earth's core. It explains why the Moon has almost no iron core of its own. The Moon is made of pieces of Earth, blasted into space by a collision, and then reassembled in orbit. And this collision might have been essential for life on Earth. The impact likely tilted Earth's axis to its current 23.5 degrees, giving us seasons. The debris from the collision might have delivered water and organic compounds to Earth's surface. The Moon's formation might have been one of the most important events in Earth's history. We exist in part because a planet-sized object crashed into the early Earth billions of years ago. Let's talk about meteor showers and why they happen at the same time every year. Meteor showers occur when Earth passes through the debris trail left by a comet. Comets are icy bodies that orbit the Sun, and as they approach the Sun, they heat up and release gas and dust. This material spreads out along the comet's orbit, forming a stream of debris. When Earth's orbit intersects with one of these debris streams, the particles enter Earth's atmosphere at high speeds, typically 30 to 70 kilometers per second. The friction with the atmosphere heats them up until they vaporize, creating streaks of light we call meteors or shooting stars. Because the debris streams follow the orbits of their parent comets, and because Earth orbits the Sun on a predictable path, we encounter the same debris streams at the same time every year. The Perseids happen every August when Earth passes through the debris from Comet Swift-Tuttle. The Leonids happen every November from debris from Comet Tempel-Tuttle. The Geminids happen every December, though their parent body is an asteroid, not a comet. These debris streams can persist for thousands of years. Some meteor showers have been recorded since ancient times. The Perseids have been observed for at least 2,000 years. When you see a shooting star, you're seeing a piece of a comet, perhaps millions of years old, burning up in Earth's atmosphere. Let's talk about the colours of stars and what they tell us. Stars come in different colours: blue, white, yellow, orange, red. The colour depends on the star's surface temperature. Blue stars are the hottest, with surface temperatures of 30,000 Kelvin or more. White stars are cooler, around 10,000 Kelvin. Yellow stars like the Sun are about 6,000 Kelvin. Orange stars are around 4,000 to 5,000 Kelvin. Red stars are the coolest, around 3,000 Kelvin. This might seem backward. Red is usually associated with heat, and blue with cold. But in physics, blue light has more energy than red light, and hotter objects emit more blue light. A piece of metal heated in a forge starts out glowing red, then orange, then yellow, then white, then blue-white as it gets hotter. Stars work the same way. The colour of a star also tells us about its mass and lifespan. Blue stars are massive and burn through their fuel quickly, lasting only a few million years. Red stars are small and burn slowly, lasting for trillions of years. Yellow stars like the Sun are in between, lasting about 10 billion years. When you look up at the night sky and see stars of different colours, you're seeing stars at different stages of their lives with different masses, temperatures and destinies. Betelgeuse, the red supergiant in Orion, is nearing the end of its life. It could explode as a supernova at any time, astronomically speaking. It might have already exploded and the light from the explosion is on its way to us right now. Or it might not explode for another 1,000 years. We don't know. But when it does explode, it will be spectacular. Betelgeuse is close enough that when it goes supernova, it will be visible during the day for weeks or months. It might be as bright as the full moon. It will be the most dramatic astronomical event visible from Earth in recorded history, and it could happen tomorrow, or in 1,000 years. We're waiting. Let's talk about variable stars, stars whose brightness changes over time. Some stars pulsate. They expand and contract rhythmically, changing in size and temperature and brightness. Cepheid variables are one type. They're massive, bright stars that pulsate with periods ranging from a few days to several months. The period of pulsation is related to the star's intrinsic brightness, which makes Cepheids incredibly useful for measuring distances in the universe. If you observe a Cepheid and measure its period, you can calculate how bright it actually is. Then you compare that to how bright it appears from Earth, and the difference tells you how far away it is. This is called the cosmic distance ladder, and Cepheids are one of the most important rungs. Henrietta Swan Leavitt discovered the relationship between Cepheid period and luminosity in 1912 while working at Harvard College Observatory. She was analysing photographic plates of the Small Magellanic Cloud, a dwarf galaxy near the Milky Way, and she noticed that brighter Cepheids had longer periods. This discovery became one of the foundations of modern cosmology. Edwin Hubble used Cepheids to prove that the Andromeda Nebula was actually a separate galaxy far beyond the Milky Way. This fundamentally changed our understanding of the universe. Before Hubble, many astronomers thought the Milky Way was the entire universe. After Hubble, we knew the universe was much, much larger. One woman, analysing photographic plates by hand, discovered the tool that would reveal the true scale of the cosmos. Let's talk about binary stars, because most stars aren't alone. About half of all stars are in binary or multiple star systems. They orbit each other, bound by gravity. Some binaries are very wide, with the stars separated by thousands of astronomical units. Some are very close, orbiting each other in hours or days. Close binary systems can interact in strange ways. If one star expands into a red giant, It might overflow its gravitational boundary and dump material onto its companion. This mass transfer can cause the companion star to spin up, heat up, or even explode. Some binary systems contain a white dwarf and a normal star. The white dwarf pulls material off its companion, and this material accumulates on the white dwarf's surface. Eventually, enough material builds up that it undergoes runaway fusion in a nova explosion. The white dwarf isn't destroyed, but it releases an enormous amount of energy in a brief, bright outburst. If the white dwarf accumulates too much mass and exceeds about 1.4 solar masses, it collapses and then explodes completely in a Type Ia supernova. These supernovae are remarkably consistent in brightness, which makes them useful for measuring cosmic distances. They're one of the tools we use to study the expansion of the universe and the nature of dark energy. Binary stars are laboratories for extreme physics. They let us study mass transfer, accretion, tidal interactions, and stellar evolution in ways we couldn't with single stars. Let's talk about globular clusters, which are some of the oldest structures in the universe. A globular cluster is a spherical collection of stars, typically containing tens of thousands to millions of stars packed tightly together. The stars in a globular cluster are all roughly the same age and composition, formed from the same cloud of gas billions of years ago. Globular clusters orbit galaxies in extended halos. The Milky Way has about 150 known globular clusters orbiting it. Some are close to the galactic center, some are far out in the halo, hundreds of thousands of light years away. The stars in globular clusters are old, very old. Some are nearly as old as the universe itself, 12 or 13 billion years old. They formed in the early universe when there were fewer heavy elements, so their stars are metal poor compared to stars in the galactic disk. Globular clusters are beautiful. When you look at images of them, you see this dense ball of stars, hundreds of thousands of suns packed into a region only a few dozen light years across. In the center of a globular cluster, stars are separated by distances of light days or light weeks instead of light years. The night sky on a planet in a globular cluster would be filled with bright stars, hundreds or thousands of them brighter than Venus appears from Earth. But globular clusters are also violent. Stars in the core pass close to each other frequently, and these encounters can eject stars from the cluster or disrupt binary systems. Over billions of years, globular clusters gradually evaporate as stars are ejected one by one. These clusters are relics from the early universe, slowly dissolving as the universe ages. Let's talk about open clusters, which are younger and less tightly bound than globular clusters. Open clusters are loose collections of stars, typically containing a few hundred to a few thousand stars. They form in the spiral arms of galaxies from collapsing clouds of gas and dust. The stars in an open cluster are young, often just a few million to a few 100 million years old. The Pleiades, also known as the Seven Sisters, is a famous open cluster visible to the naked eye. It contains several hundred stars, and the brightest ones are hot blue giants. The cluster is only about 100 million years old, practically newborn by cosmic standards. Open clusters don't last long. The stars are not tightly bound by gravity, and over time, gravitational interactions with other stars and molecular clouds in the galaxy pull the cluster apart. Most open clusters dissolve within a few 100 million years, and their stars disperse into the general stellar population of the galaxy. The Sun likely formed in an open cluster billions of years ago. Its siblings are now scattered across the galaxy, indistinguishable from other stars. Somewhere out there are stars that formed from the same molecular cloud as the Sun, stars that are the Sun's brothers and sisters. But we don't know which ones they are. They've drifted too far apart, mixed in with all the other stars in the galaxy. Let's talk about the interstellar medium. the gas and dust between the stars. Space isn't empty. Even in the regions between stars there's gas and dust. Not much, about 1 atom per cubic centimetre on average, but it's there. In some regions, molecular clouds, the density is much higher, maybe 1,000 or 1,000,000 atoms per cubic centimetre. These molecular clouds are where stars form. Gravity pulls the gas and dust together, and the cloud collapses. As it collapses, it fragments into smaller clumps, and each clump can form a star or a star system. The remaining material forms a disk around the young star, and planets can form from this disk. The interstellar medium is also enriched over time by dying stars. When stars die, they release the heavy elements they created through fusion back into space. Supernovae, planetary nebulae, stellar winds, all of these processes return material to the interstellar medium. This material gets incorporated into the next generation of stars. The Sun is a second or third generation star. The atoms in the Sun, and in you, were created in earlier generations of stars that lived and died billions of years ago. The iron in your blood was created in a supernova. The calcium in your bones was created in a dying star's final moments. You're made of the remnants of dead stars. The interstellar medium is the universe's recycling system. Stars are born from it, live, die, and return their material to it, and the cycle begins again. Let's talk about the shape of the Milky Way, because it's not just a random collection of stars. The Milky Way is a spiral galaxy. It has a central bulge, a disk, and spiral arms extending from the centre. The disk is about 100,000 light-years across and about 1,000 light-years thick. The central bulge is a dense region of old stars. The spiral arms contain younger stars, gas and dust. We're located in the disk, about 26,000 light-years from the galactic centre, in a minor spiral arm called the Orion arm. When you look up at the night sky and see the Milky Way stretching across the sky, you're looking edge-on through the disk of the galaxy. You're seeing the combined light of billions of stars too faint and distant to see individually. The Milky Way is rotating. Different parts rotate at different speeds, because galaxies don't rotate like solid objects. The Sun orbits the galactic centre at about 220 kilometers per second, completing one orbit every 230 million years. The last time the Sun was in its current position in the galaxy, dinosaurs had just started to appear on Earth. The Milky Way also has a dark matter halo extending far beyond the visible disk. This halo contains most of the galaxy's mass, but we can't see it. We only know it's there because of its gravitational effects on the stars and gas in the galaxy. The Milky Way is our home galaxy. It's where we live, where all the stars we see with the naked eye are located, where the Sun and all its planets exist. And it's just one galaxy among trillions. Let's talk about the Andromeda Galaxy, our nearest large galactic neighbour. Andromeda is a spiral galaxy similar to the Milky Way, but somewhat larger. It's about 2.5 million light-years away, which makes it one of the farthest objects visible to the naked eye. On a dark night, away from city lights, you can see Andromeda as a faint, fuzzy patch of light in the constellation Andromeda. That fuzzy patch contains about 1 trillion stars. When you look at Andromeda with the naked eye, you're seeing the combined light of 1 trillion suns, so distant that their light has been travelling for 2.5 million years to reach your eyes. Andromeda and the Milky Way are approaching each other at about 110 kilometers per second. In about 4.5 billion years they will collide. Well, collide isn't quite the right word. The stars in both galaxies are so far apart that almost no stars will actually hit each other. But the galaxies will pass through each other, and their gravitational interactions will disrupt both galaxies, pulling out long tidal tails of stars and gas. Over hundreds of millions of years, the two galaxies will merge, forming a larger elliptical galaxy. The night sky will be dramatically different. Instead of the Milky Way, future astronomers will see a more diffuse collection of stars. The Sun might be ejected from the galactic core into the halo, or it might remain near the centre. We don't know exactly what will happen to the solar system, but it will probably survive the merger intact. By the time the collision happens, the Sun will have expanded into a red giant, and the Earth will likely be uninhabitable or destroyed. But if humanity or our descendants still exist, they'll witness one of the most spectacular events in the universe, the merger of two galaxies. Let's talk about the local group, the collection of galaxies that includes the Milky Way and Andromeda. The local group contains about 80 known galaxies. Most of them are small dwarf galaxies orbiting the Milky Way or Andromeda. The large and small Magellanic Clouds, visible from the southern hemisphere, are dwarf galaxies orbiting the Milky Way. They're close enough that they're being tidally disrupted by the Milky Way's gravity, and they're slowly being pulled apart. The local group is about 10 million light-years across. It's gravitationally bound, meaning the galaxies are held together by their mutual gravitational attraction. As the universe expands, galaxy clusters and groups are pulled apart, but the local group is bound tightly enough that it won't be torn apart by cosmic expansion. Eventually, most of the galaxies in the local group will merge with either the Milky Way or Andromeda. The local group is part of a larger structure called the Laniakea supercluster, which contains about 100,000 galaxies spread across 420 million light-years. But even Laniakea is just a small part of the large-scale structure of the universe. Let's talk about galaxy clusters and superclusters, the largest gravitationally bound structures in the universe. Galaxy clusters are collections of hundreds or thousands of galaxies bound together by gravity. The Virgo cluster, about 53 million light-years away, contains over 1,000 galaxies. The Coma cluster contains over 1,000 galaxies. These clusters are massive, containing more mass than 1,000 trillion suns. Most of the mass in galaxy clusters is not in galaxies, it's in dark matter. The galaxies themselves only account for about 2% of the total mass. Dark matter makes up about 80%. The rest is hot gas filling the space between galaxies, emitting X-rays. Galaxy clusters are useful for studying dark matter because they're massive enough that they bend light from background objects through gravitational lensing. By studying how light is bent, astronomers can map the distribution of dark matter in the cluster, even though they can't see the dark matter directly. Superclusters are even larger structures, collections of galaxy clusters and groups. But superclusters are not gravitationally bound. They're just regions where galaxy clusters happen to be closer together. The cosmic expansion will eventually pull superclusters apart. The largest structures in the universe are cosmic filaments, enormous strands of galaxies separated by vast voids. These filaments can be hundreds of millions of light-years long. They form a cosmic web, with filaments intersecting at massive galaxy clusters and enormous voids in between. This is the large-scale structure of the universe. It's not uniform, it's a web of filaments and voids shaped by gravity and dark matter and the expansion of the universe. Let's talk about cosmic voids, the empty regions between filaments. Voids are enormous regions of space with very few galaxies. Some voids are over 100 million light-year across. They're not completely empty, but they're much less dense than the average regions of space. Where a typical region might contain dozens of galaxies, a void might contain only one or two. Voids form because of the way gravity works. In the early universe, small density fluctuations grew over time. Denser regions attracted more matter and became denser still. Less dense regions lost matter to the denser regions and became less dense. Over billions of years, this process created the filaments and voids we see today. If you were in a galaxy in the middle of a void, the night sky would be very dark. There would be almost no nearby galaxies. You'd have to look billions of light years away to see other galaxies, and they'd be faint and distant. It would be a lonely place. Voids are fascinating because they are almost entirely dominated by dark energy. There's so little matter in voids that dark energy's repulsive effect is strongest there. Voids expand faster than the average regions of the universe, pushing galaxies away and making the voids even larger over time. Let's talk about quasars, some of the brightest and most distant objects in the universe. Quasars are extremely luminous active galactic nuclei powered by supermassive black holes. They're found in distant galaxies, billions of light years away, and they're so bright that they outshine their entire host galaxies. A single quasar can be brighter than 1 trillion stars. The light from quasars comes from the accretion disk around the supermassive black hole. As material falls toward the black hole, it heats up to millions of degrees and emits enormous amounts of radiation. The accretion disk is relatively small, maybe only a few light days across, but it produces as much light as an entire galaxy. Quasars were more common in the early universe. Most of the quasars we observe are very distant, which means we're seeing them as they were billions of years ago. In the local universe, there are very few quasars. This suggests that quasars were a phase that galaxies went through when they were young, and their central black holes were actively feeding on large amounts of gas. The Milky Way's central black hole, Sagittarius A, is relatively quiet now. It's not accreting much material. But billions of years ago it might have been a quasar, shining brightly and visible from across the universe. Let's talk about gravitational waves, ripples in the fabric of space-time itself. When massive objects accelerate, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves. They were predicted by Einstein's general relativity, but they weren't directly detected until 2015. In September 2015, the LIGO detectors in the United States detected gravitational waves from the merger of two black holes about 1.3 billion light-years away. The two black holes, each about 30 times the mass of the Sun, spiraled into each other and merged, releasing more energy and gravitational waves in a fraction of a second than all the stars in the observable universe emit in light. The gravitational waves travelled across 1.3 billion light-years of space and caused the LIGO detectors to move by less than the width of a proton. That's how sensitive these detectors are. They can measure changes in distance smaller than the size of an atomic nucleus. Since that first detection, LIGO and other gravitational wave observatories have detected dozens of black hole mergers, neutron star mergers, and other events. Gravitational wave astronomy is a new way of observing the universe, letting us see events that don't produce light. When two neutron stars merge, they produce both gravitational waves and light. In 2017, LIGO detected gravitational waves from a neutron star merger, and telescopes around the world observed the light from the same event. This was the first time a single astronomical event was observed in both gravitational waves and electromagnetic radiation. Gravitational waves are a new window into the universe. They let us observe black holes directly, study the behaviour of matter in extreme conditions, and test general relativity in ways that weren't possible before. Let's talk about the speed of gravity, which is the same as the speed of light. If the Sun suddenly disappeared, Earth wouldn't immediately fly off into space. The gravitational influence of the Sun would continue for about 8 minutes, the same time it takes light from the Sun to reach Earth. Then, 8 minutes after the Sun vanished, Earth would stop feeling the Sun's gravity and would move in a straight line through space. Gravity doesn't act instantaneously. It propagates at the speed of light. This is a consequence of general relativity. Gravity is not a force in the traditional sense. It's the curvature of space-time caused by mass and energy. Changes in that curvature propagate as gravitational waves at the speed of light. This has been tested experimentally. When LIGO detects gravitational waves from a black hole merger, the waves arrive at the same time as the light from the event, confirming that gravity and light travel at the same speed. In Newton's theory of gravity, gravitational effects were instantaneous. If the sun disappeared, Earth would immediately feel the change. But Newton's theory is an approximation. Einstein's general relativity is more accurate, and it says that nothing, not even gravity, can propagate faster than light. Let's talk about frame dragging, one of the stranger predictions of general relativity. When a massive object rotates, it drags space-time around with it. This is called frame dragging, or the lens-thirring effect. Near a rotating black hole, space-time itself is rotating, and anything near the black hole is pulled along with it. Frame dragging is a small effect for most objects, but it's measurable. In 2004, the Gravity Probe B satellite measured frame dragging around Earth. This satellite carried gyroscopes that were incredibly sensitive to changes in orientation. By measuring how the gyroscope's axis shifted over time, scientists confirmed that Earth rotation drags space-time around with it. Near a rotating black hole, frame dragging is extreme. There's a region called the ergosphere, outside the event horizon, where space-time is being dragged around so fast that nothing can remain stationary. Even if you fired your rockets at full thrust, you couldn't avoid being pulled around the black hole. Space-time itself is rotating, and you're being carried with it. Black holes don't just warp space, they twist it. Let's talk about the no-hair theorem, which says that black holes are remarkably simple objects. Black holes are described by just three properties: mass, spin, and electric charge. That's it. Everything else about the black hole, all the details of what fell into it, the type of matter, the history, everything is lost. This is the no-hair theorem. Black holes have no hair, meaning no distinguishing features beyond mass, spin, and charge. You could make a black hole out of hydrogen, or iron, or old smartphones, or cats, and the resulting black hole would be exactly the same as long as the mass, spin, and charge were identical. The black hole doesn't remember what it was made from. This seems to violate information conservation, which is a fundamental principle in physics. Information shouldn't be destroyed. But if you throw a book into a black hole, the information in that book seems to be lost forever. It's reduced to just mass, spin, and charge. This is the black hole information paradox, and it's still not fully resolved. Stephen Hawking suggested that information might be encoded in the Hawking radiation emitted by black holes, but we don't fully understand how this would work. Black holes are the universe's paper shredders. They take complex objects and reduce them to the simplest possible form. Let's talk about wormholes, which are theoretical shortcuts through space-time. A wormhole is a hypothetical tunnel connecting two different points in space-time. If you entered one end of a wormhole, you'd emerge from the other end, possibly at a different location, or even a different time. Wormholes are allowed by the equations of general relativity, but that doesn't mean they exist. To keep a wormhole open, you'd need exotic matter with negative energy density. We don't know if such matter exists or can be created. Even if wormholes exist, they'd probably be tiny, maybe Planck scale, and incredibly unstable. They'd collapse almost as soon as they formed, and even if you could stabilize a wormhole and make it large enough to travel through, you'd face enormous tidal forces that would tear you apart. Wormholes are a staple of science fiction, but in reality they're probably impossible, or at least we have no idea how to make one or find one. They remain in the realm of theoretical physics, interesting to think about but likely forever out of reach. Let's talk about white holes. the theoretical opposite of black holes. A white hole is a region of space-time that nothing can enter, but from which matter and light can escape. It's the time reverse of a black hole. While black holes have event horizons you can cross but never escape, white holes have event horizons you can never cross but from which things can emerge. White holes are allowed by the equations of general relativity, just like black holes. But we've never observed one, and there are good reasons to think they don't exist. A white hole would violate the second law of thermodynamics by decreasing entropy. It would be an object that spontaneously creates order from chaos, which doesn't happen in nature. Some scientists have speculated that the Big Bang itself might have been a white hole, an event from which all the matter and energy in the universe emerged. But this is highly speculative. White holes are mathematically interesting, but probably not physically real. The universe has black holes, but it probably doesn't have white holes. Let's talk about naked singularities, which would be singularities without event horizons. Inside a black hole, there's a singularity, a point where the curvature of space-time becomes infinite and the known laws of physics break down. The singularity is hidden behind the event horizon, so we can never see it. This is the cosmic censorship hypothesis. Singularities are always hidden inside event horizons. But is this always true? Could there be naked singularities, singularities without event horizons? If a naked singularity existed, we could observe it directly. We could see a region where the laws of physics break down. Most physicists think naked singularities probably don't exist. The cosmic censorship hypothesis seems to hold in all the scenarios we've studied, but we can't prove it. It's possible that under certain extreme conditions, a singularity could form without an event horizon. If naked singularities exist, they would be among the strangest objects in the universe, places where causality breaks down and physics as we understand it ceases to function. Let's talk about the multiverse, the idea that our universe is just one of many. There are several different versions of the multiverse hypothesis. One comes from inflation, the rapid expansion of space in the first moments after the Big Bang. Inflation might not have happened everywhere at the same time. It might have happened in different regions at different times, creating separate bubble universes within a larger multiverse. Another version comes from quantum mechanics. In the many worlds interpretation, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. This would create an enormous, constantly branching multiverse of parallel universes. Another version comes from string theory, which suggests there might be many different possible configurations of the extra dimensions, each corresponding to a different universe with different laws of physics. All of these multiverse hypotheses are speculative. We have no direct evidence for other universes, and by definition, if other universes exist beyond our cosmic horizon, we can never observe them. This makes the multiverse hypothesis difficult or impossible to test, which bothers some scientists who prefer theories that make testable predictions. But the multiverse is an interesting idea. It would explain the apparent fine-tuning of our universe. If there are countless universes with different physical constants, it's not surprising that at least one of them has the right conditions for life. We exist in this universe because the conditions allow us to exist. In universes where the conditions are different, there's nobody there to wonder why. Let's talk about the holographic principle, one of the strangest ideas in theoretical physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume. A three-dimensional region of space can be completely described by information on a two-dimensional surface surrounding it. This comes from studying black holes. The entropy of a black hole, which is related to the amount of information it contains, is proportional to the area of its event horizon, not its volume. This suggests that the information in the black hole is somehow encoded on its surface. Some physicists have extended this idea to the entire universe. Maybe the three-dimensional universe we experience is actually a hologram, a projection from information encoded on a distant two-dimensional surface. This is deeply weird and hard to visualize, but it's a serious idea in theoretical physics, and it might help reconcile quantum mechanics and general relativity. If the holographic principle is true, reality is even stranger than we thought. Let's talk about cosmic strings, hypothetical one-dimensional defects in space-time. Cosmic strings are predicted by some theories of the early universe. They're incredibly thin, maybe as thin as a proton, but incredibly dense. A cosmic string 1 meter long might weigh as much as the Earth. Cosmic strings would be remnants from phase transitions in the early universe, similar to the way cracks can form in ice as water freezes. If cosmic strings exist, they would stretch across vast distances, maybe even across the entire observable universe. A cosmic string passing near Earth would have strange gravitational effects. Light passing on opposite sides of a cosmic string would be deflected, creating double images of distant objects. Spacecraft passing through a cosmic string would be torn apart by tidal forces. We've never observed a cosmic string, and they might not exist at all. But if they do, they would be among the most exotic objects in the universe. Let's talk about domain walls, another type of hypothetical cosmic defect. Domain walls are two-dimensional surfaces that might have formed during phase transitions in the early universe. They would be regions where the properties of space change discontinuously, like the boundary between two different phases of matter. Domain walls, if they exist, would have enormous energy densities. They would affect the expansion of the universe and the formation of large-scale structures. But we haven't seen any evidence for domain walls, and most cosmological models suggest they probably don't exist. Or if they do, they're rare and far away. Cosmic strings and domain walls are examples of topological defects, structures that can form when symmetry is broken during phase transitions. They're interesting theoretical possibilities, but we have no direct evidence for them. Let's talk about the anthropic principle again, but from a different angle. The weak anthropic principle simply observes that we exist, therefore the universe must have properties compatible with our existence. This is a tautology. It's true, but it doesn't explain anything. The strong anthropic principle suggests that the universe must have properties that allow life to develop at some point, because observers are necessary for the universe to exist or be meaningful. This edges into philosophy and metaphysics. Some interpretations of quantum mechanics suggest that observation is necessary to collapse quantum wave functions and make reality definite. If that's true, then a universe without observers might never become fully real. It would remain in a state of superposition, never crystallizing into concrete existence. This is speculative and controversial. Most physicists think the universe existed before observers appeared and would continue to exist without them. But it's an interesting idea to contemplate. Does the universe need observers? Or are we just here by chance, temporarily witnessing a cosmos that doesn't care whether we exist? Let's talk about the simulation hypothesis, the idea that we might be living in a computer simulation. If it's possible to create realistic simulations of conscious beings, and if civilizations tend to create many such simulations, then there would be far more simulated consciousnesses than real ones. Statistically, you would be more likely to be in a simulation than in base reality. This argument, popularized by philosopher Nick Bostrom, has three possible conclusions. Either civilizations always destroy themselves before they can create realistic simulations, or they choose not to create such simulations, or we are almost certainly in a simulation. There's no way to prove or disprove the simulation hypothesis. If the simulation is good enough, it would be indistinguishable from reality. We might live in a simulated universe and never know. Some people find this idea disturbing, others find it strangely comforting. If we're in a simulation, then maybe death isn't the end. Maybe we're just characters in a cosmic video game, and when we die, we respawn or continue in some other form. Or maybe we're not in a simulation at all. Maybe this is base reality, the only reality, and we're not virtual beings running on some alien supercomputer. We can't know. And maybe it doesn't matter. Whether real or simulated, this is the reality we experience, and we have to live in it. Let's talk about the heat death of the universe in more detail, because it's the most likely fate of everything. In the far future, after all the stars have burned out and all the black holes have evaporated, the universe will be cold and dark. The temperature will approach absolute zero. Space will be filled with photons, stretched to infinitely long wavelengths by the expansion of space and dark energy, continuing to push everything apart. Nothing will happen. There will be no stars, no planets, no life, no change, no processes, no events. The universe will have reached maximum entropy, a state of perfect disorder where nothing can happen because there's no energy gradient to drive any process. This is heat death. Not a dramatic end, but a slow fade into nothingness. The universe won't end. It will just continue existing, empty and unchanging, for eternity. Some scientists have speculated about whether anything could survive heat death. Could advanced civilizations find ways to harness the last dregs of energy and persist somehow? Could consciousness exist in some form in an endlessly cold and dark universe? Probably not. The laws of thermodynamics are strict. When the universe reaches heat death, nothing complex can exist. No thought, no computation, no life. Just particles drifting apart forever in an expanding void. The universe will become a silent, empty, eternal tomb. Everything that ever existed will be gone, not destroyed, but dissolved into maximum entropy. This won't happen for trillions upon trillions of years, but it will happen, eventually. Let's talk about Boltzmann brains one more time because the concept bothers me. If the universe exists for infinite time, then eventually random fluctuations will create anything, including conscious brains with false memories. These Boltzmann brains would vastly outnumber evolved brains like yours statistically. This creates a philosophical problem. If Boltzmann brains are possible, then your memories your entire life might be false. You might have spontaneously formed 1 second ago with fake memories of a past that never happened, and you'll disintegrate back into chaos 1 second from now. Most physicists think this doesn't happen because the universe isn't infinite in time, or because quantum mechanics prevents Boltzmann brains from forming, or because we're misunderstanding something fundamental about how the universe works. But the possibility remains, unsettling and unfalsifiable. Are you real? Am I real? Or are we just temporary fluctuations in an infinite sea of chaos, dreaming of a universe that doesn't exist? Probably not. Probably we're real, evolved beings in a real universe, but probably is not the same as certainly. Let's talk about the philosophy of time, because physics has some strange things to say about it. In our everyday experience, time flows from past to future. We remember the past, but not the future. We age in one direction. Eggs break, but don't spontaneously unbreak. Time has an arrow, but the fundamental laws of physics are time-symmetric. If you filmed particles interacting and played the video backward, you couldn't tell. The backward version would obey the same laws as the forward version. There's no fundamental arrow of time in the equations. The arrow of time comes from thermodynamics, from the fact that entropy increases. The universe started in a low entropy state, and it's been moving toward higher entropy ever since. That's why eggs break and don't unbreak. It's far more likely for an egg to go from a low entropy state, intact, to a high entropy state, broken, than the reverse. But this raises a question. Why did the universe start in a low entropy state? Why wasn't it already at maximum entropy? We don't know. This is one of the deep mysteries of cosmology. Some physicists have suggested that time might not be fundamental. Maybe time emerges from some deeper structure, something more basic than time itself. Maybe at the most fundamental level, the universe is timeless, and time only emerges in certain contexts. These are speculative ideas, but they're being seriously explored. We might not understand time as well as we think we do. Let's talk about consciousness and the universe, a topic that combines physics, philosophy, and neuroscience. Consciousness is a mystery. We know it exists because we experience it, but we don't know what it is or how it arises from physical processes. How do neurons firing in a brain create subjective experience? Why does it feel like something to be you? This is the hard problem of consciousness, and nobody has solved it. We can study the brain and map its activity, but we can't explain why brain activity produces conscious experience. Some theories suggest that consciousness might be more fundamental than we think. Maybe consciousness is a basic feature of the universe, like space or time or energy. Maybe all matter has some degree of consciousness, and complex brains just concentrate it. This is panpsychism, and it's controversial. Most neuroscientists think consciousness emerges from complex information processing, not from some fundamental property of matter. But we don't know for sure. There's also the question of whether consciousness affects physics. In some interpretations of quantum mechanics, observation collapses wave functions. Does that mean consciousness plays a role in determining reality? Or is observation just a technical term for any interaction that causes decoherence, with no special role for conscious observers? We don't know. Consciousness remains one of the great unsolved mysteries, and its relationship to physics, if any, is unclear. Let's talk about the fine structure constant, one of the fundamental constants of nature. The fine structure constant, usually written as alpha, is a dimensionless number approximately equal to a 137. It describes the strength of the electromagnetic interaction between elementary particles. What's weird about alpha is that it's dimensionless. It's a pure number, not dependent on any particular system of units. You could measure it in meters or feet or light years, and you'd get the same value. It seems to be a fundamental property of the universe. Richard Feynman called alpha one of the greatest damn mysteries of physics. We don't know why it has the value it does. We can measure it precisely, but we can't derive it from any deeper theory. It seems to be just a fact about the universe, a number that had to be set when the universe began. If alpha was slightly different, chemistry would be different. Atoms would be different sizes. Chemical bonds would have different strengths. Life as we know it wouldn't be possible. Alpha is one of about 20 fundamental constants that seem to be fine-tuned for life. We don't know why. Maybe it's just luck. Maybe there's a deeper theory that explains why these constants have the values they do. Maybe there's a multiverse, and we happen to live in a universe where the constants allow for life. Or maybe there's something we're missing, some deeper understanding that would make it all make sense. Let's talk about the Planck length, the smallest meaningful length in physics. The Planck length is about 1.6610⁻35 meters. It's incredibly tiny. If an atom were magnified to the size of the observable universe, the Planck length would be about the size of a tree. The Planck length is the scale at which quantum mechanics and gravity both become important. Below the Planck length, our current theories of physics break down. We would need a theory of quantum gravity to describe what happens at those scales. Some physicists think space itself might be quantized at the Planck scale. Space might not be continuous, but made of discrete units, like pixels on a screen. If so, the Planck length would be the size of 1 pixel of space. This is speculative. We have no experimental evidence for quantized space, but it's a possibility that several theories of quantum gravity, including loop quantum gravity and string theory, explore. If space is quantized, then there's a smallest possible distance, and it doesn't make sense to talk about anything smaller than the Planck length. Space would have a fundamental graininess at the tiniest scales. Let's talk about the Planck time, the smallest meaningful interval of time. The Planck time is about 5.4 10^{-4 seconds. It's the time it takes light to travel 1 Planck length. Before this time, after the Big Bang, our current physics doesn't apply. We don't know what happened in the first Planck time of the universe's existence. The Planck time is so short that it's hard to comprehend. A second contains more Planck times than there have been seconds since the Big Bang. Just as the Planck length might represent the smallest possible distance, the Planck time might represent the smallest possible duration. Below the Planck time, the concept of time might not even make sense. Let's talk about what might have caused the Big Bang, though this ventures into pure speculation. We don't know what caused the Big Bang, or if cause even makes sense in this context. If time itself began with the Big Bang, then there was no before in which something could cause it. The Big Bang might have been the beginning of everything: space, time, matter, energy, causality itself. Some theories suggest the Big Bang was a quantum fluctuation, a spontaneous event allowed by quantum mechanics. Others suggest it was part of a cycle, with the universe expanding and contracting repeatedly. Others suggest it emerged from a pre-existing multiverse. But all of these are speculative. We have no evidence for what happened before the Big Bang, or even if before the Big Bang is a meaningful concept. The Big Bang might be the ultimate boundary of scientific knowledge. We can study what happened after it, but what happened before, or what caused it, might be forever beyond our reach. Let's talk about why there's something rather than nothing, the most fundamental question in philosophy. Why does the universe exist at all? Why is there something rather than nothing? This question has bothered philosophers for thousands of years, and physics doesn't have a good answer. Some have suggested that nothing is unstable and inevitably produces something through quantum fluctuations. Others suggest that existence is necessary, that a universe must exist for logical or mathematical reasons we don't understand. Others think the question is meaningless. If there were nothing, there would be nobody to ask why there's nothing. We exist, therefore the universe exists, and that's all there is to it. But it still feels like there should be an explanation. The universe exists. That's remarkable. That's the most remarkable fact there is. And we don't know why. Maybe we'll never know. Maybe the existence of the universe is a brute fact, something that just is, with no deeper explanation. Or maybe someday we'll understand. Maybe future physicists or philosophers will discover why the universe had to exist, why nothing was never an option. Until then, the question remains as mysterious and profound as ever. Let's talk about the observable universe versus the whole universe, because this distinction matters. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's about 93 billion light-years in diameter. Beyond that, there's more universe. But we can't see it because the light hasn't had time to reach us yet. How much more universe is there beyond what we can see? We don't know. The universe might be infinite or it might be finite, but so large that the observable universe is just a tiny fraction of the whole. If the universe is infinite, then there are infinite copies of everything. Infinite copies of you. Infinite copies of Earth. Infinite variations on every possible arrangement of matter. Somewhere out there, in an infinite universe, there's a version of Earth where everything is identical except you're wearing different socks. This is disturbing and fascinating. In an infinite universe, everything that can happen does happen infinitely many times. But we don't know if the universe is infinite. We can only observe a finite region. The rest is beyond our cosmic horizon, forever inaccessible. We live in a universe that might be infinite, but we can only see a finite part of it. The full extent of reality might be forever beyond our reach. Let's talk about cosmic horizons and how they limit what we can know. There are several types of cosmic horizons. The particle horizon is the boundary of the observable universe, the distance beyond which we can't see because light hasn't had time to reach us. The event horizon is the boundary beyond which we can never receive information, even if we wait forever, because cosmic expansion is carrying those regions away faster than light can bridge the gap. As the universe expands and dark energy dominates, the event horizon is shrinking. Galaxies that are currently visible will eventually cross the event horizon and disappear from view. In the far future, astronomers will only be able to see galaxies in our local group. The rest of the universe will have receded beyond the event horizon, and there will be no way to ever observe them again. This means that future civilizations, if they exist, will have less information about the universe than we do. They'll look up at the sky and see a smaller, emptier universe. They might conclude that their galaxy is alone, that nothing exists beyond it. We live at a special time in cosmic history, and we can still see a large fraction of the universe. In the future, that won't be true. The universe is becoming more lonely and isolated as expansion accelerates. Let's talk about the role of mathematics in describing the universe. Physics is written in the language of mathematics. The fundamental laws of nature are mathematical equations. General relativity, quantum mechanics, electromagnetism, all of it is mathematics. This raises a philosophical question. Why is the universe mathematical? Why does it follow precise mathematical rules? Is mathematics something we invented to describe the universe? Or is it something we discovered, something fundamental to the structure of reality? Some physicists and philosophers think mathematics is the fundamental reality, and the physical universe is just a manifestation of mathematical structures. This is the mathematical universe hypothesis, proposed by physicist Max Tegmark. If the mathematical universe hypothesis is true, then every logically consistent mathematical structure exists as a physical universe somewhere in a vast multiverse. Our universe is one of these structures, and we experience it as physical reality. This is speculative and difficult to test, but it's an interesting idea. Maybe reality is fundamentally mathematical, and physics is just applied mathematics, the study of one particular mathematical structure that happens to exist. Let's talk about entropy and disorder, and why the universe tends toward increasing entropy. The second law of thermodynamics says that entropy, a measure of disorder, always increases in a closed system. This is why things fall apart, why energy disperses, why you can't unscramble an egg. But entropy isn't just disorder. It's also a measure of the number of possible microscopic states corresponding to a macroscopic state. A broken egg has more possible arrangements of its molecules than an intact egg, so it has higher entropy. The universe started in a low entropy state and has been increasing in entropy ever since. Eventually it will reach maximum entropy, heat death, where nothing interesting can happen anymore. But why did the universe start in a low entropy state? This is a deep mystery. It's not explained by any known law of physics. The Big Bang could have started with the universe already at maximum entropy, but it didn't. Why? Some theories suggest that the low entropy initial state is related to inflation, or to the particular conditions of the Big Bang, or to the fact that gravity hasn't reached equilibrium yet. But we don't have a complete answer. The arrow of time, the fact that time flows in one direction, is intimately connected to the increase of entropy. Time flows forward because entropy increases. If entropy decreased, time would flow backward. This connection between entropy and time is profound and not fully understood. Why does entropy increase? Why does time flow in one direction? These questions are still being explored. Let's talk about the cosmic microwave background in more detail because it's one of our best tools for studying the early universe. The CMB is light from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before that, the universe was opaque, filled with hot plasma. After that, it became transparent, and the light from that moment has been travelling through space ever since. We detect the CMB as microwave radiation, with a temperature of about 2.7 Kelvin. It's remarkably uniform, the same temperature in every direction to within about 1 part in 100,000. But there are tiny fluctuations, small variations in temperature that correspond to regions that were slightly denser or less dense in the early universe. These fluctuations are the seeds of all structure. Denser regions eventually collapsed under gravity to form galaxies and galaxy clusters. Less dense regions became voids. By studying the pattern of these fluctuations, cosmologists can learn about the conditions in the early universe, the amount of dark matter and dark energy, the expansion rate, and many other properties. The CMB is a snapshot of the universe when it was 380,000 years old. It's the oldest light we can see, and it tells us about the universe's infancy. Missions like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, revealing its structure and confirming many predictions of cosmological theory. The CMB is evidence for the Big Bang, for inflation, for the existence of dark matter and dark energy. It's one of the pillars of modern cosmology. Let's talk about baryonic acoustic oscillations, another tool cosmologists use to study the universe. In the early universe, pressure waves travelled through the hot plasma, creating regions of higher and lower density. When the universe became transparent and atoms formed, these density variations were frozen into the distribution of matter. Today, we can see the imprint of these ancient sound waves in the distribution of galaxies. Galaxies are slightly more likely to be separated by a certain distance, about 500 million light-years, corresponding to the scale of the largest sound waves in the early universe. By measuring this characteristic scale, and how it changes with distance and time, cosmologists can study the expansion history of the universe and the effects of dark energy. Baryonic acoustic oscillations are like a cosmic ruler, a standard length scale imprinted in the structure of the universe that we can use to measure distances and study cosmology. Let's talk about Type Ia supernovae, which are used to measure cosmic distances. Type Ia supernovae occur when a white dwarf in a binary system accumulates enough mass to exceed about 1.4 solar masses, the Chandrasekhar limit. The white dwarf collapses and then explodes in a thermonuclear explosion. Because the mass at which this happens is always about the same, Type Ia supernovae have a consistent peak brightness. This makes them useful as standard candles for measuring distances. If you observe a Type Ia supernova and measure its apparent brightness, you can calculate how far away it is. In the 1990s, 2 teams of astronomers used Type Ia supernovae to measure the expansion rate of the universe at different distances and times. They expected to find that the expansion was slowing down due to gravity. Instead, they found that the expansion was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than expected, meaning the universe had expanded more than predicted. This was the discovery of dark energy and the accelerating expansion of the universe. Type Ia supernovae are among the most important tools in observational cosmology. They've helped us measure the expansion rate, discover dark energy, and study the history of the universe. Let's talk about standard candles and standard rulers, the two main methods for measuring cosmic distances. A standard candle is an object with a known intrinsic brightness. By measuring how bright it appears, you can calculate how far away it is. Type Ia, supernovae, and Cepheid variables are standard candles. A standard ruler is an object with a known size. By measuring how large it appears, you can calculate its distance. Baryonic acoustic oscillations are a standard ruler. Using standard candles and rulers, astronomers have built up a cosmic distance ladder, a series of methods for measuring distances at different scales. Nearby objects can be measured using parallax, the apparent shift in position as Earth orbits the Sun. More distant objects require Cepheid variables. Even more distant objects require type Ia supernovae. The farthest objects require baryonic acoustic oscillations or other techniques. Each method has uncertainties, and the uncertainties add up as you go to larger distances. Measuring cosmic distances is difficult and requires careful calibration, but over decades of work, astronomers have built up a consistent picture of the universe's scale and expansion history. Let's talk about redshift as a tool for measuring distance and velocity. When astronomers measure the redshift of a galaxy, they're measuring how much the light has been stretched by the expansion of space. A redshift of Z1 means the wavelength has been stretched by a factor of 2. A redshift of Z2 means a factor of 3. For nearby galaxies, redshift corresponds directly to velocity through the Doppler effect. For distant galaxies, it's more complicated because the expansion of space itself is stretching the light. The highest redshift objects we've observed are galaxies at redshift of Z13 or so, seen as they were less than 400 million years after the Big Bang. The James Webb Space Telescope is designed to observe even higher redshifts, looking for the first galaxies that formed in the universe. Redshift is one of the most important measurements in cosmology. It tells us how far away an object is, how fast it's moving, and how long ago the light we're seeing was emitted. Let's talk about the first stars, population 3 stars, which have never been directly observed. The first stars formed about 100 to 200 million years after the Big Bang, in a universe that contained only hydrogen, helium, and tiny amounts of lithium. There were no heavy elements yet because heavy elements are created in stars, and no stars had lived and died yet. These first stars, called population 3 stars, were probably very massive, perhaps 100 to 1,000 times the mass of the Sun. They burned hot and fast, living only a few million years before exploding as supernovae. When they exploded, they seeded the universe with the first heavy elements: carbon, oxygen, iron. All the elements necessary for planets and life were created in these first stars and scattered into space. We've never directly observed a population 3 star. They're too far away and too faint. But we can study their effects on the early universe, and we can infer their properties from theory. The James Webb Space Telescope might be able to detect signs of population 3 stars in the very early universe. If we can find them, we'll learn about the conditions in the first few 100 million years after the Big Bang. These were the stars that lit up the universe for the first time, ending the cosmic dark ages and beginning the era of galaxies and structure. Let's talk about the dark ages of the universe, the period between the CMB and the first stars. After the universe became transparent at 380,000 years, it entered a period called the Dark Ages. There were no stars yet, no sources of light except the fading glow of the CMB. The universe was dark and cold, filled with hydrogen and helium gas slowly collapsing under gravity. This period lasted for about 100 to 200 million years. During this time, the first structures began to form. Gas collapsed into clumps, and the clumps grew denser and hotter until they ignited as the first stars. The Dark Ages ended when the first stars turned on. Their light ionized the surrounding hydrogen, creating bubbles of ionized gas. Over time, these bubbles grew and merged, and eventually the entire universe was reionized. We can't see the Dark Ages directly because there were no sources of light, but we can study them indirectly through their effects on the CMB and through radio observations of hydrogen. The Dark Ages were a critical period in the universe's history, the time when the seeds of all structure were planted. Let's talk about reionization, when the first stars and galaxies ionized the hydrogen in the universe. After the Dark Ages, the first stars formed and began emitting ultraviolet radiation. This radiation was energetic enough to ionize hydrogen, stripping electrons from hydrogen atoms and turning the gas into a plasma. Reionization wasn't instantaneous. It happened gradually, over hundreds of millions of years, as more and more stars formed and their ionizing radiation spread through the universe. By about 1 billion years after the Big Bang, reionization was complete. The universe was once again filled with ionized hydrogen, as it had been before atoms formed. But this time, the ionization was caused by stars, not the hot plasma of the early universe. Reionization is one of the major transitions in the universe's history. It marks the end of the Dark Ages and the beginning of the era of galaxies. We're still studying reionization, trying to understand exactly when it happened, how fast it happened, and what types of objects were responsible. Was it primarily massive stars, or were there other sources like quasars or exotic objects? The James Webb Space Telescope is helping us answer these questions by observing the earliest galaxies and studying their properties. Let's talk about the cosmic web, the large-scale structure of the universe. On the larger scales, the universe is organized into a web-like structure. Galaxies are clustered along filaments, with vast voids in between. Where filaments intersect, you find massive galaxy clusters. This structure formed from the tiny density fluctuations in the early universe. Denser regions attracted more matter and became denser still, while less dense regions lost matter and became voids. The cosmic web is shaped by dark matter. Dark matter provides most of the gravity that pulls normal matter into filaments and clusters. Simulations of structure formation that include dark matter produce cosmic webs that match what we observe. The filaments of the cosmic web can be hundreds of millions of light-years long. The voids can be just as large. Its structure on a scale that's hard to comprehend, and the cosmic web is still evolving. Filaments are growing, voids are expanding, clusters are merging. The universe is not static. It's a dynamic, evolving structure on all scales. Let's talk about the local universe, the region within about 100 million light-years of the Milky Way. The local universe contains thousands of galaxies, including the Local Group, the Virgo Cluster, and many smaller groups and clusters. We can study these galaxies in detail because they're relatively nearby. The local universe is our cosmic neighborhood. These are the galaxies we can observe with ground-based telescopes, the galaxies where we can resolve individual stars, the galaxies we understand best. Beyond about 100 million light-years, galaxies become more difficult to study. We can still observe them, but we can't see individual stars anymore. We have to study them as integrated wholes, using their total light and spectral features. The local universe is where we test our theories of galaxy formation, stellar evolution, and cosmic structure. It's the laboratory for extragalactic astronomy. Let's talk about the Great Attractor, a gravitational anomaly in the local universe. The Milky Way and nearby galaxies are moving toward a region of space in the direction of the constellation Centaurus at about 600 kilometers per second. This motion is caused by the gravitational pull of a massive concentration of matter called the Great Attractor. The Great Attractor is about 250 million light-years away, and it contains the mass of tens of thousands of galaxies. But we can't see it directly because it's behind the plane of the Milky Way, obscured by gas and dust. Beyond the Great Attractor, there's an even larger structure called the Shapley supercluster, which is pulling on the Great Attractor and on us. These large-scale flows of galaxies reveal the distribution of mass in the universe. By studying how galaxies move, we can map out the dark matter and understand the structure of the cosmic web. The Great Attractor is a reminder that the universe is not homogeneous on all scales. There are local concentrations of mass that affect the motion of galaxies, pulling them in different directions. Let's talk about galaxy mergers, which are common events in the universe. Galaxies collide and merge all the time. The Milky Way is currently in the process of absorbing several small dwarf galaxies. In a few billion years, it will merge with Andromeda. When galaxies merge, their stars don't collide because stars are so far apart. But the gravitational interactions disrupt both galaxies, pulling out long tidal tails of stars and triggering bursts of star formation as gas clouds collide and compress. Over hundreds of millions of years, the two galaxies settle down and merge into a single, larger galaxy. If both galaxies have supermassive black holes at their centers, the black holes will eventually merge as well, releasing gravitational waves. Galaxy mergers are one of the main ways galaxies grow. Small galaxies merge to form larger galaxies. Large galaxies absorb smaller galaxies. Over billions of years, this process builds up the massive elliptical galaxies we see in the centers of galaxy clusters. Mergers also affect star formation. The gravitational interactions during a merger can trigger intense bursts of star formation, creating millions of new stars in a relatively short time. But mergers can also shut down star formation by heating or ejecting the gas needed to make stars. Galaxy evolution is driven by mergers, gas accretion, star formation, and feedback from supernova and black holes. It's a complex, ongoing process. Let's talk about active galactic nuclei and how they affect their host galaxies. Active galactic nuclei, or AGN, are powered by supermassive black holes actively accreting matter. As matter falls into the black hole, it heats up and emits enormous amounts of energy, sometimes outshining the entire galaxy. This energy doesn't just radiate into space, it interacts with the surrounding gas, heating it, pushing it around, sometimes driving powerful winds or jets that can extend for hundreds of thousands of light years. These winds and jets can affect star formation in the galaxy. By heating or expelling gas, AGN feedback can shut down star formation. This is thought to be one of the reasons why the most massive galaxies have stopped forming stars. Their central black holes grew large and active, and the feedback from the AGN blew out or heated all the gas, preventing further star formation. AGN feedback is one of the key processes in galaxy evolution. It regulates how large galaxies can grow and helps explain the observed relationship between black hole mass and galaxy mass. Supermassive black holes don't just sit at the centers of galaxies, they actively shape the galaxies around them. Let's talk about the intergalactic medium. The gas between galaxies. The space between galaxies isn't empty. It's filled with hot, diffuse gas, mostly hydrogen and helium, at densities of about 1 atom per cubic meter. This gas is ionized and heated to temperatures of millions of degrees. The intergalactic medium contains more mass than all the stars in all the galaxies combined. Most of the ordinary matter in the universe is not in stars or planets. It's in this hot, diffuse gas between galaxies. We can study the intergalactic medium by observing how it absorbs light from distant quasars. The gas leaves characteristic absorption lines in quasar spectra, called the Lyman alpha forest. The intergalactic medium is also where galaxies get their gas. As galaxies move through the intergalactic medium, they can accrete gas from it, fueling new star formation. Over time, the intergalactic medium is slowly being incorporated into galaxies or pushed into voids by cosmic expansion. but right now it's the dominant reservoir of normal matter in the universe. Let's talk about metallicity, the abundance of elements heavier than helium in astronomical objects. In astronomy, metals means anything heavier than helium. Carbon, oxygen, iron, everything. The universe started with just hydrogen, helium, and a tiny bit of lithium. All the heavier elements were created later in stars. The first stars had zero metallicity. They were made purely of primordial hydrogen and helium. When they exploded, they enriched the surrounding gas with metals. The next generation of stars formed from this enriched gas and had non-zero metallicity. Over billions of years, successive generations of stars have created more and more heavy elements, gradually increasing the metallicity of the interstellar medium. Metallicity is a clock. By measuring the metallicity of a star or a galaxy, we can estimate its age. Low metallicity stars are old, formed early in the universe's history. High metallicity stars are younger, formed from gas enriched by many previous generations of stars. The Sun has roughly solar metallicity, meaning about 2% of its mass is elements heavier than helium. This is typical for stars in the Milky Way's disk formed a few billion years ago. The most metal-poor stars have metallicities 100,000 times lower than the Sun. They're ancient, among the oldest stars in the galaxy, formed when the universe was young and barely enriched. Let's talk about stellar populations and how they tell the history of galaxies. Astronomers classify stars into populations based on their age and metallicity. Population I stars are young and metal-rich, found in the disks of spiral galaxies. Population II stars are old and metal-poor, found in globular clusters and galactic halos. Population III stars are hypothetical primordial stars with zero metallicity. By studying the stellar populations in a galaxy, astronomers can reconstruct its star formation history. When did it form most of its stars? Has star formation been continuous or bursty? Has it recently merged with another galaxy? Elliptical galaxies tend to have old stellar populations. They formed most of their stars billions of years ago and have been quiescent ever since. Spiral galaxies have a mix of old and young stars. They've been forming stars continuously for billions of years. Dwarf galaxies can have diverse star formation histories. Some formed stars early and then stopped. Others have been forming stars continuously. Some have had recent bursts of star formation triggered by interactions with other galaxies. Stellar populations are a record of a galaxy's life, written in the ages and compositions of its stars. Let's talk about how galaxies get their gas and how they lose it. Galaxies form stars from gas, mostly hydrogen. But where does the gas come from? And why do some galaxies have lots of gas while others have almost none? Gas comes from several sources. Galaxies can accrete gas from the intergalactic medium. They can acquire gas by merging with other galaxies. They can recycle gas from dying stars, which return some of their mass to the interstellar medium. Galaxies lose gas through star formation, which converts gas into stars. They lose gas through outflows driven by supernovae and AGN, which can expel gas from the galaxy entirely. They can lose gas to other galaxies during interactions. The balance between gas inflow and outflow determines how long a galaxy can continue forming stars. If a galaxy runs out of gas, star formation stops. The galaxy becomes quenched. Massive elliptical galaxies are quenched. They have little gas and little star formation. Spiral galaxies like the Milky Way are still forming stars because they still have gas. Understanding how galaxies acquire and lose gas is key to understanding galaxy evolution. Let's talk about star formation rates and how they've changed over cosmic time. The star formation rate in the universe was much higher in the past than it is now. About 10 billion years ago, galaxies were forming stars at rates 10 times higher than today. This era, sometimes called cosmic noon, was the peak of star formation in the universe. Most of the stars that exist today were formed during this period. Since then, the star formation rate has been declining. Galaxies are running out of gas, or their gas is being heated or expelled, or cosmic expansion is making it harder for galaxies to accrete new gas. The universe is slowly winding down. Star formation is decreasing. Eventually, in the far future, all the gas will be used up or expelled, and no new stars will form. The universe will be filled with aging stars and dead remnants. We live at a time when the universe is still forming stars, but much less vigorously than in the past. We're in the slow decline toward a starless future. Let's talk about the cosmic star formation history and what it tells us. By observing galaxies at different distances, we're seeing them at different times in the past. Distant galaxies are young. Nearby galaxies are old. By measuring the star formation rates in galaxies at different distances, astronomers can reconstruct the history of star formation in the universe. The results show that star formation peaked about 10 billion years ago and has been declining since. This decline is related to the increase in dark energy and the accelerating expansion. As expansion accelerates, it becomes harder for galaxies to pull in gas from the intergalactic medium, and star formation declines. The cosmic star formation history is one of the key observational constraints on theories of galaxy formation and evolution. Let's talk about how the universe's chemistry has changed over time. The early universe was almost entirely hydrogen and helium. Over time, stars created heavier elements through fusion and scattered them into space through supernovae and stellar winds. The metallicity of the universe has been gradually increasing as more and more stars live and die. The interstellar medium today is much more metal-rich than it was billions of years ago. This has consequences for planet formation. Rocky planets like Earth require heavy elements to form. In the early universe, there weren't enough heavy elements to make rocky planets. Earth-like planets could only form after several generations of stars had enriched the interstellar medium with metals. This suggests that life, which requires complex chemistry and probably requires rocky planets, could not have appeared until several billion years after the Big Bang. We might be among the earliest civilizations in the universe, living soon after the universe became capable of supporting life. Or we might not. We don't know how common life is or how long it takes to evolve, but the universe's increasing metallicity means that conditions for life have been improving over time. Let's talk about the future of the Milky Way. In about 4 to 5 billion years, the Milky Way will collide with Andromeda. The two galaxies will merge over a period of a few billion years, forming a larger elliptical galaxy sometimes nicknamed Milkomeda. The Sun will probably survive the merger. The solar system might be flung into the outer halo of the merged galaxy, or it might remain near the centre. Either way, the Sun will be old by then, nearing the end of its main sequence lifetime. After the merger with Andromeda, Milkomeda will gradually absorb the other galaxies in the local group. Over tens of billions of years, the local group will merge into a single massive elliptical galaxy. Meanwhile, the rest of the universe will be receding due to cosmic expansion. Eventually, Milkomeda will be alone, surrounded by darkness. The observable universe will shrink to include only our own galaxy and whatever remains of the local group. This is the future of the Milky Way: merger, isolation, and eventual fading as its stars age and die. Let's talk about the stars you can see with the naked eye, because they're all nearby. When you look up at the night sky and see stars, you're seeing stars in our local neighbourhood, within a few thousand light years. The farthest naked eye stars are perhaps 15,000 or 20,000 light years away, in exceptional cases. Most of the stars you see are within a few hundred light years. They're bright because they're either intrinsically luminous, like giants and supergiants, or because they're close, like nearby main sequence stars. All the stars you can see with the naked eye are in the Milky Way. You're not seeing other galaxies when you look at individual stars. The only exception is Andromeda, which appears as a faint fuzzy patch, not as individual stars. When you look up at the night sky, you're seeing a tiny, tiny fraction of the Milky Way. Most of the galaxy is too far and too faint to see, and most of the universe is completely invisible without telescopes. But those few thousand visible stars have captured human imagination for millennia. We've named them, connected them into constellations, used them for navigation, told stories about them. The night sky is our window into the universe, limited but beautiful. Let's talk about the constellations and why they're arbitrary. Constellations are patterns we imagine in the sky, connecting stars that appear close together from our perspective, but are actually at vastly different distances. Orion's belt, for example, consists of 3 stars, Alnitak, Alnilam and Mintaka. Alnitak is about 800 light-years away. Alnilam is about 2,000 light-years away. Mintaka is about 900 light-years away. They're not a physical group, they just happen to lie along the same line of sight from Earth. If you travelled to another star system and looked back at Earth's sky, the constellations would be completely different. The stars would be rearranged into new patterns. Constellations are human inventions, meaningful to us but arbitrary from a cosmic perspective. Different cultures have drawn different constellations from the same stars. The ancient Greeks saw a hunter in Orion. Other cultures saw different figures. There's no objective truth to what a constellation is. It's whatever pattern we imagine. But constellations are useful. They help us navigate the night sky, identify stars and tell stories. They're a way of organising and making sense of the overwhelming number of stars. Let's talk about the zodiac and why it exists. The zodiac constellations are the 12 constellations that lie along the ecliptic, the path the sun appears to follow across the sky over the course of a year. This path exists because Earth orbits the sun. From our perspective on Earth, the sun appears to move against the background of distant stars. Over a year, the sun traces a complete circle through the sky, passing through the 12 zodiac constellations. The planets also appear to move along the ecliptic because the solar system is mostly flat. All the planets orbit the sun in roughly the same plane, so from Earth they appear to move through the same band of constellations. This made the zodiac constellations important in ancient astronomy and astrology. They were the constellations where interesting things happened, where planets appeared, where eclipses occurred. Astrology is not science. The positions of planets in zodiac constellations don't affect your personality or your future. But the zodiac constellations are real astronomical features, a consequence of Earth's orbit and the geometry of the solar system. Let's talk about precession, the slow wobble of Earth's axis. Earth's axis is tilted about 23.5 degrees and it wobbles like a spinning top. This wobble is called precession, and it takes about 26,000 years to complete one cycle. Precession means that the position of the North Celestial Pole changes over time. Right now, the North Celestial Pole is near Polaris, the North Star, but 13,000 years from now, it will be near Vega, and 26,000 years from now, it will be back near Polaris. Precession also means that the equinoxes, the points where the sun crosses the celestial equator, shift slowly westward along the ecliptic. This is called the precession of the equinoxes. Precession is caused by the gravitational pull of the sun and moon on Earth's equatorial bulge. It's a slow effect, about 50 arcseconds per year, but over thousands of years it adds up. Precession is why the astrological zodiac is out of sync with the astronomical zodiac. Astrology was developed thousands of years ago when the sun appeared in different constellations at different times of year, but precession has shifted everything by about one constellation. If you're an astrological Aries, the sun was probably actually in Pisces when you were born. Let's talk about the celestial sphere, the imaginary sphere on which all celestial objects appear to lie. From our perspective on Earth, the stars appear to be attached to a giant sphere surrounding us. This is the celestial sphere, and it's a useful concept for navigating the night sky and understanding astronomical coordinates. The celestial sphere rotates once per day because Earth rotates. Stars rise in the east and set in the west. The sun, moon, and planets move against the background of stars along the ecliptic. The celestial sphere is divided into constellations, and celestial objects are located using coordinates, right ascension and declination, analogous to longitude and latitude on Earth. The celestial sphere is an illusion. The stars are not all the same distance from us. They're at vastly different distances scattered throughout the Milky Way. But from our perspective, they appear to lie on a sphere, and it's convenient to treat them that way for the purpose of navigation and observation. Let's talk about light pollution and how it affects our view of the night sky. In urban areas, artificial lights brighten the night sky, washing out faint stars and making it difficult to see the Milky Way or other faint objects. Light pollution is a growing problem. As cities expand and lighting becomes more widespread, the night sky becomes less and less visible. Many people have never seen the Milky Way because they've never been in a location dark enough. This is a loss. The night sky is part of our heritage, part of what makes us human. For thousands of years, humans have looked up at the stars and wondered. Now, many people can't see them. Light pollution also affects wildlife. Many species rely on natural light cycles, and artificial light can disrupt their behaviour. There are efforts to reduce light pollution by using better designed lighting that directs light downward instead of upward, and by reducing unnecessary lighting. Dark sky preserves have been established to protect areas with minimal light pollution. If you ever get the chance to visit a truly dark location, far from cities, do it. Look up. See the Milky Way stretching across the sky, the countless stars, the sense of depth and vastness. It's worth it. Let's talk about meteor showers and the best times to see them. Meteor showers occur when Earth passes through debris trails left by comets. The timing is predictable because Earth's orbit is consistent. The Perseids peak around August 12th, the Geminids peak around December 14th, the Leonids peak around November 17th, the Quadrantids peak around January 3rd. To see a meteor shower, you need a dark sky, away from light pollution. You need to be patient, because meteors appear sporadically, and you need to look up, not at a specific point but broadly at the sky. Meteors can appear anywhere, but they'll seem to radiate from a specific point in the sky called the radiant. For the Perseids, the radiant is in the constellation Perseus. For the Geminids, it's in Gemini. The best time to watch is usually after midnight, when your location on Earth is facing forward in Earth's orbit, so you're running into the debris stream head-on. Meteor showers are one of the easiest astronomical phenomena to observe. You don't need a telescope or any special equipment, just your eyes, a dark sky, and patience. Let's talk about the phases of the moon and why they occur. The moon doesn't produce its own light. It reflects light from the sun. As the moon orbits Earth, we see different amounts of the sunlit side, creating the phases. When the moon is between Earth and the sunlit side faces away from us, and we see the new moon, which is dark. As the moon moves in its orbit, we see more and more of the sunlit side, creating the waxing crescent, first quarter, waxing gibbous, and full moon. After the full moon, we see less and less of the sunlit side, creating the waning gibbous, last quarter, waning crescent, and back to new moon. The phases repeat every 29.5 days, the time it takes the moon to orbit Earth relative to the sun. The moon's phases have been important to human cultures for millennia. Many calendars are based on the lunar cycle. The moon has been used to mark time, plan agriculture, and navigate. Let's talk about the beauty of the night sky and what it means to us. For most of human history, the night sky was a constant presence. People knew the stars, tracked their movements, told stories about them. The night sky was a source of wonder, inspiration, and guidance. Today, many people rarely see the stars. Light pollution, urbanization, and indoor lifestyles mean that the night sky is hidden from most of humanity. But it's still there. The stars are still shining. The Milky Way still stretches across the sky. The planets still wander through the constellations. The moon still waxes and wanes. And when you do see the night sky, really see it, from a dark location, it's profound. It's a reminder of how small we are, how vast the universe is, how brief our time here is. It's humbling and beautiful and terrifying and wonderful all at once. The universe is vast and ancient and mostly empty, and we're tiny creatures on a small planet orbiting an ordinary star in an unremarkable corner of an ordinary galaxy among trillions of galaxies. But we're here. We can look up. We can wonder. We can try to understand. That's remarkable. And that's where I'll leave you tonight, or this morning, wherever you are, whenever you're listening to this. The universe is strange and beautiful and incomprehensibly vast. It's full of wonders we're only beginning to understand. Black holes and neutron stars and dark matter and dark energy and billions of galaxies and trillions of planets and mysteries we haven't even thought to ask about yet. And you're part of it. You're made of atoms forged in stars billions of years ago. You're a temporary arrangement of matter that can think and wonder and feel. You're the universe looking at itself, trying to understand itself. That's what we are. That's what all of us are. So thank you for listening. Thank you for being curious. Thank you for caring about the universe and our place in it. And if you're using this to fall asleep, I hope you've had a good journey. I hope the facts and stories have been interesting without being too stimulating. I hope you drift off thinking about the cosmos, about the vast scales of space and time, about the wonders that exist beyond our everyday experience. Sleep well. Dream of stars. The universe will still be here when you wake up, and there will always be more to learn, more to discover, more to wonder about. Good night.